Okay, well, welcome. This is part one of a two-part series. So we'll be meeting this Friday morning and next Friday morning. We broke up the agenda so it kind of would fit kind of like logically. If we get it done a little bit faster today, maybe we'll just start a little bit on next week's stuff or do a bunch of side discussions. And if we go a little long today, then some of today's stuff will be on next week. But in either case, we'll get it all covered. So here's our sponsors for today. If you weren't already aware, most of you guys probably know that this is who is sponsoring us because that's probably who invited you to attend today. So Massachusetts Energy Efficiency Partnership is who asked me to come on and do these topics. Last week we did indoor air quality and ventilation topic, and then this Friday and next Friday we're doing the energy savings for package systems. So here's our agenda today. It's three main categories: some HVAC basics as related to energy. So if you are an energy only guy, you're not really up to speed on HVAC, this will hopefully help you. And if you're an HVAC guy and you're not really understanding how your utility and energy bills and code compliance works, maybe this will help you as well. So that's our main topic. And then we're going to start diving into individual measures that'll save energy. We'll start off with easy stuff like programmable thermostats, work our way up into economizers, maybe time dependent. We'll do a little bit more rehash on demand ventilation, which we covered last week. And then next week, we'll continue on. We'll do staged air volume and VFD systems for constant volume rooftops. We'll talk about heat pump systems and how those work and when they might make sense. And we'll talk about variable refrigerant flow systems. So those are kind of our topics for the next couple days. We're starting pretty basic. And in order for us to tie HVAC into our utility bill discussion, we need to explain some stuff on your utility bill. And for you guys that work on the utility side, the next like 5 minutes will be super boring to you. But for the HVAC guys, it might be eye-opening because, believe it or not, the HVAC guys have no idea how a commercial building utility bill functions, even though they own their own buildings, right? Just like most of you guys on the energy side have no idea what goes on in the guts of a chiller, right? So the first thing to think about is that kilowatt hours and kilowatts are not the same thing. They're related, obviously, but they're not the same thing. And on your utility bill, you are paying for both of these things. Kilowatt hours is how much energy consumption you have. Kilowatts is the actual power. So power and energy aren't the same, if you didn't know that either. Energy is power over a function of time. So that's why we have kilowatts for power and kilowatt hours for energy. Like I said, your utility bill is going to be charging you for both of these things. How many kilowatt hours did you use this month? And what was your biggest power demand for the month? Because how much power your building needs is going to determine the size of service needed to be brought to your building. The wire sizing, neighborhood transformer, etc., etc. So if you need more and more power, that means there'll be requirements on the utility grid to be beefed up in your area, and you're going to have to pay for that, or the collective view in your area. So when we look at this, there's a couple ways to kind of think about it on your bill. The gray line on the chart here is showing my energy usage on a given building over the course of the month, right? So, or excuse me, the course of a day, sorry. Let me get a laser pointer out here. Right, so I got low usage early in the early hours, just whatever's going on, just emergency lights, computers that are still running, etc., etc. And as the building goes occupied, obviously my energy consumption goes up throughout the day. And as people are doing various activities, and as compressors are turning on, and as people are charging forklifts and whatever they're doing, it's going up and down. All right, and then at the end of the day, it kind of it gets down to a low end again. Whatever the highest point of the day was, or later on we'll talk about the highest point of any 15-minute period, that is going to be my demand charge, right? That's going to be the most kilowatts that I possibly needed, that I possibly drew off the grid. So even though throughout the whole day I had very little kilowatts, but at that one point in time, at whatever that was, 1 in the afternoon, I had the most, and that's going to dictate my bill and how much I'm going to pay. We'll talk about how that works. So for the demand charge on your bill, right, so we have multiple charges. We have our energy consumption, and then we have our demand charge, our KW charge. For most utilities, it's going to be the highest 15-minute peak period that you have that month. So if you do one thing in your building that month to require a lot of kilowatts, to pull a lot off the grid, That's going to determine how much you pay for that whole month. And believe it or not, it's going to actually affect you for the next 11 months after that in your bill. And we'll show you that. So it can be a pretty large portion of the utility bill. For large commercial building users, it's often half of the bill could be demand charges. Sometimes it's less, sometimes it's more, but it's a pretty big chunk. And then typically the summer is going to be higher than the winter because most of the things in your building are the same year round, but the HVAC is not. Usually in the winter, most of us are using gas-based heating systems, which don't require a lot of electricity, minimal. And in the summer, we're using compressor-based systems, which do require a lot of power. So these demand charges exist, like I mentioned, because it's going to dictate how large the wires and transformers and things are that need to be provided to your area of the community. So that means that someone has to pay for that, and most utilities are set up to be like a how do you want to word it? A regulated industry where the government's dictating how much money you can and can't make for certain things, and they have to make it equitable. So they're going to be charging people that use more in order to have service. And people that use less will pay less. And they want to incentivize you to draw less. Now, if a utility, if you might think of it like, oh, well, don't they want to sell me more power? Yes, they want to sell you more power. But they want to sell it to you during the non-peak times, right? When it's easy for them to get it to you. They don't want you drawing more power at the peak times because then they have to beef up the infrastructure and the grid, which costs a lot of money. So that's why there's these demand charges. It's to incentivize you, the building user, to not draw as much power at a given amount of time. They'd much rather have you turning some loads on at night than have you turning them on in the afternoon when it's super hot. Kind of another way to think about it for you guys that are unfamiliar, if we go to your car example, you have a speedometer and an odometer, right? One of them is telling you the speed, like the instantaneous thing that is happening at that moment in relation to the miles, in this case, miles per hour. And the other one is telling you the long-term thing that's happening in terms of your miles, your odometer, right? It's going to be very similar with my kilowatts, which is going to be my instantaneous snapshot in time. And then I have my kilowatt hours, which is going to be my cumulative thing over time. So if we look at two customers, customer A and customer B, because we're really creative with the naming over here. One of them has a 50 kilowatt load that they're going to run this week for 50 hours. The other one has a 5 kilowatt load that they're going to turn on for 500 hours. Right? From an energy standpoint, 50 times 50 is 2,500 kilowatt hours, and 5 times 500 is 2,500 kilowatt hours. They're both going to buy the exact same amount of kilowatt hours. However, one's going to have a 50 kW demand, the other's going to have a 5 kW demand. So on this particular utility bill, they're paying 15 cents a kilowatt hour. So that's $375 for either customer, and they're paying a $28 demand charge. So that's $1,400 for customer A, but it's only $140 for customer B because they have a much lower demand. They're using the same amount of kilowatt hours over the course of that, let's say whatever that is, course of the time frame. But one of them is taking it all in one big chunk. The other one's taking it slowly over time. So it's going to be a big difference on your bill. So if you're customer A, you want to start making your bill look more like customer B. You'd rather not have all of your load come on at once to give you this giant demand charge. You'd rather trickle it out and have it happen more uniformly. We'll look at a specific utility bill. This utility happens to provide both electric and gas. This one is Madison, Wisconsin, which oddly is not where I live or where most of you guys live, but happens to be the bill that I had on my computer, so that's the one I used. When I start looking at the breakdown of this particular bill, there are a couple of things to notice. We'll just stick on the top half right now, which is the electric side. The bottom half is the gas bill. But you have multiple charges on here. You have charges for your actual kilowatts that we talked about, the demand. We have kilowatt hours, the amount of usage that I have, total for the whole month. And then I also have distribution-related charges. Right? So I have charges for distribution and charges for the actual electricity. And I don't know about you guys, but where I live residentially, it works the same way. I have to pay for the grid, my distribution charge, and I have to pay for my actual consumption. And in my case, I pay two different entities. It's all in one bill, but I pay ComEd, who's my distribution provider, and then I just blinked out and forgot who my and then AEP is my provider for my actual energy. It's all delivered by ComEd on their grid, but you can source it to whoever you want. In any case, you're paying for all these different things. So if we look at the demand charges on here, the demand charge is going to show up in two different places. First off, it's showing up under my electrical consumption as my maximum on-peak demand. In this case, for this customer, it was 95.7 kilowatts. That was their peak. They're paying 42 cents rate for that, so it's $1,200 out of their $4,400 bill. Their electric bill is $4,400 if you look there on the right side, and they paid $1,200 on this demand charge for their electric service. But then if you also look under the distribution side of their bill, they also have a demand charge, and that one's 99.2 kilowatts for another $252 because that one's at 8-cent rate. So they're paying it over here on the electrical side, and they're paying it on the demand side. And if you notice, it's not the same number, right? If you look at my notes on here, the demand charge under the service side, the 95.7, that's the highest peak that I had that month. But the demand charge is the highest peak that I've had this month or the preceding 11 months. So that 99.2 didn't happen this month in September. It must have happened a couple months ago. So I'm going to pay that 99.2 for the whole entire year times this rate, 8 cents, every single month. Unless my service side gets above 99.2, then that becomes my new highest scenario, and I pay that one for 12 months. So if you make one mistake and turn a bunch of loads on at the same time, you could be paying for it for 12 months repeatedly over and over. You definitely don't want to do that. You definitely want to pay attention to the demand side. I had that extra screenshot of the bill in there. There are lots of things we can do to reduce demand. We'll talk about a few of them. Our main goal today is not talking about demand charges and reducing demand. It's about saving energy. But if I can do both with the same measures, the same technology to get both jobs done, why not, right? One way that demand charges are reduced is what's called load shedding, or nowadays we typically call it demand response. We called it load shedding back in the 90s when I started. For some reason, that name evolved away. There's different ways to do that, like on chiller plants and things like that. But today we're talking about package systems, which means typically rooftop units or possibly DX air handler splits. So on package systems, you have limited options on how you can do something with the utility actively involved in telling you when to turn stuff off. So if we have a day where it's hot outside or whatever other thing is generating the demand problem, the utility will contact people that they've already contracted with and ask them to turn stuff off. In the old days, it was literally the phone call to the building service engineers at some giant, plant like Caterpillar or whoever, and saying, "Hey, can you guys shut down production today? We're going to cut you a $38,000 check just to shut the plant down and send everybody home. We need you guys offline. You guys are drawing too much," right? Nowadays, it's done a little bit differently, and it's done through automation. But for small buildings, which are the kind that have package systems, we can't contact every building operator and tell them that. So what ends up happening is you have technology taking care of that. One way to do that is through the thermostat, in what's typically referred to as an open ADR, automated demand response. The utility sends a signal to the thermostat and tells the thermostat, "Hey, we're in a demand event today from 2 to 4 p.m. Can you do something about that? Can you spread your set points a couple degrees? Instead of cooling your building down to 73, why don't you only cool it down to 75, right? And we'll pay you something for that. We'll give you either for that event or for that to be part of that program." So like in my own house, residentially, I've been on a demand response program for 6 years, and they pay me $10 a month, which is, at this point in time, $240 they've given me to be on the program, and they can shut off my unit for up to 2 hours at a time. They don't do it very frequently, but they have that right because I signed up for that program. But that can happen at commercial buildings as well. The utility can send a signal to the thermostat to go into demand response. Personally, I'm not a big fan of this. I just told you I do it at my house, but I'm super cheap and I do everything to save money. And I have some things that I do to compensate for being on the demand response situation. But we'll talk about that at a different time. But at a commercial building, I'm not a super big fan of this, because if I could relax my set point from 73 to 75 and my employees can be just as productive, why am I only doing what the utility asks me to? Why not just do it all the time? Just always go to 75, right? So obviously I don't do that because 75 won't work for my customers. They won't be comfortable, or my clients or my tenants, or however you want to look at it. So I don't do that. So if I do it when the utility asks, it's going to lead people to be disgruntled. And when they're disgruntled, they walk around and bitch about it, and they stand at the water cooler and complain about it, and they're just not very productive people at that point. So I'm not a huge fan of doing it this way. There's a lot of other ways to do it. It also reduces my ability to dehumidify, and it could cause some short cycling my equipment if it's not set up correctly. Usually it's set up correctly, so no big deal, but it does hurt my dehumidification ability as well. And the reason I don't like messing with people is because people are everything. In an office building type environment or something like that, the people costs are massive. So on the left here, if you look over here, in blue is how much it costs me to build my building. Purple is how much energy it costs me to operate my building for the life of the building. Red is how much it costs me to maintain the building for the life of the building. Green is all my property taxes, which that's not very exciting, but you have to pay it. But if I take those four things and I add the salary of the people working there to the puzzle, those four things smush into this little wedge over here on the right side. All of those things, energy costs included, are completely irrelevant related to the cost of people. So I want to do whatever I can to save on my energy bill without the people noticing it. I don't want the occupants to even know I'm saving energy. I mean, I don't mind if they know I'm saving energy, but I don't want them to feel it in terms of their HVAC comfort. So I would rather do things behind the scenes to save energy and to save demand versus just shutting off their thermostat or putting their set point really high and then they complain about it and they're not productive. So where's the opportunity to fix some of these buildings? How do we bridge the gap between the energy bill and the HVAC package systems here? So the first thing to realize is that the target is existing buildings. New construction is great, but there's not a lot of new construction relative to how many existing buildings we have in the United States, especially not in established areas like in the Northeast where many of you guys are from, or even in the Midwest where I'm from. Yeah, if you go out to somewhere that's expanding and sprawling, that's different. But most of these dense urban areas, like a Boston, a New York, a Chicago, a Philadelphia, there's not a lot of new construction. There's like gut rehab type stuff, but there's not a lot of brand new buildings going up relative to the existing buildings. The other thing is the new buildings are all going to be theoretically complying with the current energy codes in their entirety. So they're going to be reasonably efficient compared to some of the older buildings. So I really want to put my focus on the older buildings because there's just a lot of them and they are fairly big energy pigs. So that's my target, existing buildings. Now I may use the new construction guidelines and recommendations to rehab an existing building. That's totally fine and probably a good idea. So if I want to save energy in a building, specifically related to HVAC, I first have to identify where these areas of improvement are. I got to consider how the HVAC behaves with the other systems. For example, if I retrofit your building with new lights, I take out a bunch of T8s or T12s or whatever it is you have, take out a bunch of fluorescent bulbs, and I put LEDs in, which is an extremely common scenario the past 5 years, right? If I do that, those LED lights don't give off as much heat, right? Just like at your house, you might have an old bulb somewhere in one of your lamps that has an incandescent 100-watt bulb. Turn that thing on for 2-3 minutes, then go grab it with your hand. Tell me how that feels. Versus your LED light that you have on all your other lamps. You can hold that thing in your hand, you could caress it, you could give it a little kiss with your lips if you want. It's not hot at all. So older style lighting is putting off a lot of heat, which causes my HVAC system to have to cool that building down more, do more work, if you will, because of the waste heat off of the lighting system. And the same thing with computers and other electronics and things in the building. The newer stuff typically gives off less heat than the older stuff. Like even your TV. You might have had a CRT tube TV growing up as a kid, and that thing got hot, real hot, right? And now you have some kind of flat panel LCD, and there's like almost no heat at hardly anything at all. Same with your laptop. Your laptop is barely warm compared to what your old school desktop was 15 years ago. And the same thing will happen not just with lighting, but with the building enclosure, the tightness of the building, the quality of the windows, how well the windows are sealed, the insulation levels. All of these things interact with HVAC. So it's not like HVAC exists in its own bubble. It's very interactive with the other systems in the building. So I got to consider all of that, and we'll talk about that kind of as we go through pieces of this. I want to identify the things that aren't going to cost me any money to fix, or cost me very little money to fix. No cost is pretty tough. Like if nothing else, I need somebody's time, labor time, to go deal with the thing, even if I don't have to buy anything. So let's just call it low cost improvements. If there's things I can do that are fairly easy, let's do those things first, and then worry about things that require a large capital investment and require somebody to sign off on a big budget expenditure. Let's do the easy stuff first and get that knocked out. So when I'm identifying where I can make these improvements, there are some documents that I might want to get my hands on. on older buildings, and sometimes even newer buildings, it's going to be hard to get this stuff, and if you can't get it, you can't get it, right? But ideally, you'd like to find the plans and specs from either the original building or the last time the building was really kind of gut and rehabbed. That'd be the most ideal thing. And the sequence of operation of how the controls are supposed to work, and then even more important than both of those things, the as-built drawings. Right? So the plan and specs are what the engineer and architect wanted us to build. The as-built drawings are what the mechanical and electrical contractors actually built. So I'd rather get my hands on that stuff. But if I can get my hands on that stuff, I can do things to try to return this building back to the way it was designed and originally built, right? So believe it or not, after 20 years, a lot of stuff, especially HVAC, is not 20 years, heck, after 20 months, a lot of stuff is not operating the way it was supposed to operate. And maybe the changes were made for the better, but probably they weren't. They were probably made to solve some specific Band-Aid problem that somebody had in one area, and it thereby is doing something to mess up the rest of the building. And then somebody reacts to that, and somebody reacts to that. A lot of times just getting a building back to its original specs is a huge benefit in terms of energy and comfort and frustration. And then maybe there's still a couple problems, but at least you kind of got back to what somebody put a lot of effort into designing. You want to do some kind of audit of the building. This doesn't have to be anything completely robust. It doesn't have to be like a top tier ASHRAE level audit, although that's totally fine, obviously. But sometimes it's just a matter of you walk in the building. Maybe you're walking it with your mechanical contractor and a representative from the utility that's on the energy performance side, right? Maybe it's just you three people walking the building and identifying what you even have in the building. And sometimes it's really obvious stuff. Like you might just walk the building with the HVAC guy and they'll be like, "Oh my God, I can't believe you still have one of those. Those have been obsoleted for like 40 years. That thing's such an energy pig." And you're like, "I don't even know what that is," right? It could be something like that, right? But just a basic walkthrough is a great place to start, and it only takes you like 3 hours to do that for an average size building. So it's a little bit of time just to kind of get an idea of what's going on. At some point, as you get more involved in this, though, you'd like to benchmark the building, like to start comparing it to something. Either compare the building's energy now to what it was, either compare the building's energy now to what it's going to be, compare it to other buildings. You can use the Energy Star Portfolio Manager, where you can basically track your building and compare it to similar buildings. But you want some kind of baseline so you can thereby set some kind of goals on what you want to get to and what's actually achievable. One of the ways to get a lot of all that stuff done is commissioning the building. And I listed on here recommissioning and retro commissioning. And it's kind of like the same thing in terms of what you're physically doing, but just its perspective on how it's being done. So recommissioning implies the building was ever commissioned before. Like it was commissioned once or more than once. And now you're going to go back and recommission it again. And that's a good idea. If you commissioned a building 5 years ago, things are totally out of sync by now. People touched a bunch of stuff they shouldn't have touched. It wouldn't be the worst thing to have a commissioning agent come in and recommission it. Retro commissioning is the same labor and same kind of effort. It just more implies that it's never been commissioned before, which is very common for a lot of buildings, especially the smaller buildings we're talking about today that have packaged HVAC systems. Somebody threw those systems in, and they tweaked a couple things and they walked away, and nobody really commissioned the whole building. Now, when I say commission, I am referring to it in the modern version with a commissioning authority, somebody who's certified to do commissioning. There's 3 or 4 agencies that certify people. And this person is not employed by the HVAC contractor or the electrical contractor or anybody on the construction team whatsoever. This person is either employed by the building owner directly or by somebody on the design team like the architect or engineer. So I want somebody who didn't set the building up, who didn't do physical work in the building. I want that kind of person to come in and commission the building. Because the person that set it up, they're going to be really hard pressed to find any flaws because they're perfect, right? If I set it up, why would I think that I did something wrong, right? So I'm going to be kind of blind to my errors. I want somebody else to come in and double check my work and babysit my work. Now, if you're a building owner, you might be thinking like, well, why the hell do I got to pay somebody to come in to babysit somebody else? It's kind of stupid, right? Why can't they just do it right the first time? Well, most of them are doing it right the first time. They just may not have a good idea of what right means, right? And even if you do have to babysit someone, it's still way cheaper to babysit someone usually than it is to let the building just operate poorly for 20 years. You definitely want to look into commissioning services. And you can also do some monitoring tools. It could be stuff where you're using tools to just measure something once, right? Just to kind of see where you're at. Or it could be stuff that's continuously monitoring. For example, on HVAC, I may want to go get some static pressure readings on all my air handlers. I could do that continuously. I can install a manometer or a magnehelic gauge or a digital pressure sensor and have it track pressure continuously. And that may be fine, and maybe I want to pay to do that. Or maybe just twice a year when I do my maintenance on my air handling systems and my coil cleaning and whatever, maybe those times I want to just check static pressure and note it in the log. And then if it's changing over time, I can be like, why is it not what it used to be 3 years ago, kind of thing. So it can be kind of an instantaneous snapshot, or it can be a continuous monitoring type tool. I gave pressure as an example, but you can do the same things with temperatures and humidities and things like that. I don't know if I said it early on, but if you guys have questions, just type them in. I'll be happy to answer them. We have enough time built in where we can go on some side tangents, as long as it's kind of related to what we're talking about. And this is a 3-hour topic, and I didn't mention it, but like halfway through, we'll take like a 10-minute break so everybody can go, fill up the coffee and all that stuff. And, so I can fill up the coffee for myself and hit the bathroom. And then whatever you guys do, that's on you. So the interaction of the HVAC with the other building systems, the two biggest things that we're thinking about in this regard are the lighting and the envelope. And those things can have a massive effect on the system. I would like to upgrade the lighting and or the building envelope before the HVAC. I'm telling you that, and I work for an HVAC distributor in my spare time. Actually, that's my day job. Teaching classes over here is my spare time. So obviously, my company likes to sell HVAC equipment. And as an HVAC distributor, I tell people, fix your lighting first. Then come back to me with the HVAC thing next year, right? Because if I can get the lighting load down, both the electrical load and the waste heat load off the lighting, it's going to allow me to install a smaller replacement cooling system in your building. And you're thinking, well, if he works for an HVAC distributor, why would he want to install something smaller? Doesn't he make less money? Well, first off, I'm not in sales either way, so I don't make any of the money. But second off, as our company, we'd rather sell you something smaller and less expensive, knowing it's going to work better, than sell you something bigger that we made money off of that you call us and complain about all the time because it's not right. So if you install the big cooling system, then you go ahead and reduce all your lighting load and building envelope load and everything like that, and now the cooling system's too big, it's going to cause humidity problems, and now you're not going to be happy with the HVAC system, even though it was basically caused by the lighting and envelope getting smaller. So do the lighting and envelope stuff first. The more efficient the lighting fixture, the smaller the cooling load is going to be, and we can deal with that. By the way, it doesn't change your heating load, right? So the lights put off less waste heat, which means I need a smaller cooling system. It doesn't mean I need a bigger heating system. Because if you didn't know it, when we do load calculations, which is what we call the heat loss, heat gain calculation of the building to figure out how much heating and cooling it gains and loses during various times of the year. For cooling, we do that calculation on a summer day, sometime in the afternoon, at a peak scenario when it's very hot outside, like 91 degrees or something like that. And we'll go through that more in a little bit. But that's my cooling scenario. Every person's in the building, every light's on, the sun's beating on the building, it's the hot day of the year. Then I calculate my cooling. For heating, I go the worst case the other way. Worst case for heating is that it's a super cold day outside. It's like 0 or whatever, right? It's a cold day outside. No one's in the building giving off body heat. None of the lights are on, right? And there is no solar. It's nighttime. That's the worst case for heating. So changing the lighting doesn't affect my heating load calculation. Now, it will mean my heating will run a little bit more, but it doesn't change my calculation for sizing it, because my calculation is based on the worst case scenario, which means all the lights are off. So it's going to reduce my cooling load requirement. And it can be quite substantial. Lighting used to be a giant portion of cooling loads when we had, like 1 watt per square foot of load coming off of that thing. Now with LED lights, it's so minimal. It's a giant savings. And lighting is no longer the largest portion of our cooling needs. Here's some general guidelines for you. This is not even code compliant. This is just simple upgrade. So this actually comes from the ASHRAE Advanced Energy Design Guide, which are guides that they put out to do better than ASHRAE 90.1 1999 version, I believe it was, which would have been like the 2001 IECC code. This was just to get you better than that. So this is basically it's a simple document. If you haven't seen it, they're free. And you can just read the section that applies to your building type, and it just gives you a list of stuff to do. Do all of these things, and you'll be whatever it was, 30% better than the 1999 code, right? And a lot of the buildings we're talking about were built before then. So doing this kind of stuff is a pretty nice upgrade. Obviously, we want to do even better than that and go to the energy code. But if you're looking for easy, quick things, just pulling up one of these cheat sheets is a simple thing to do. And beating this lighting on this list is super easy now with the LEDs. Building envelope is the other one that interacts with HVAC quite a bit. Commercial buildings don't have, what's the best way to say it without sounding stupid? At your house, residentially, getting a very high R value for your attic and your walls is very important in terms of how much heat your house loses or how much heat it gains in the summertime. It's not as big of a deal in a commercial building. I'm not saying it's not important. I'm not saying it's not involved. But the bigger your building is, the less interesting the insulation becomes to my overall heating and cooling needs. Because the bigger the building gets, that means the interior core is larger. And if you didn't know it, in a commercial building, once you get about 15 feet from the exterior wall, you get to the middle of the building, we don't have any need for heat at all. There's literally zero heat. So when we help design buildings at my office, and it's a large, office building, the interior of the building, we provide them cooling year-round on 0-degree days. They never need any heat. Because if you think about it, if I'm in the middle of the building, the people on the left of me, right of me, front, back, up, and down they're all San Diego. It's 72 degrees in all those places. So why do I need the heat? I'm not losing any heat. Everybody around me is 72. So what do I care? I don't have any heat gain, any heat loss. So I don't put heating in the interior of buildings. So the bigger the building gets, that means I have a much larger core, which means my ratio of building perimeter to interior continues to change. Now, if it's a little tiny building, like it's some little, some little corner bank, right? Well, okay, the whole bank's only 30 feet wide, so basically the whole bank is perimeter. So then that's more like your house, and insulation becomes a more interesting discussion. I'm not saying you don't need insulation. I'm not saying it's not important. I'm just saying it's not like your house where you really need to crank it up. Getting it to a decent, level of insulation is not as challenging, right? So here, the recommendation at a kind of a minimum was if you can get at least like R11 into the walls and like R20 up in the roof, you're in pretty good shape for most commercial buildings. If you can do better than that, that's okay. And if you're complying with code on a new construction building, it's going to be a little stricter than this. But if you can at least get to these levels, that puts you at a good point in terms of your HVAC upgrade. Same kind of thing with the windows, but the windows it's a little more important than the wall insulation in a commercial building because the windows, in a lot of commercial buildings, we have a lot of glass. Now, if you're in older buildings, you probably don't have a lot of glass. If you're in a building right now that was built, well, right now you're probably at home because nobody's actually at their buildings. But if your office building that you normally work at was built before World War II, it's probably really thick walls with a lot of masonry and small windows. And everybody has a perimeter window. It's probably in an H or an L or a C shape in order to get everybody a perimeter with a window. But the windows are probably relatively small to the building because we want the thermal mass of the building to keep the building cool because we didn't have any cooling, right? If you're built in stuff in the 1960s and later, there's tons and tons of glass because air conditioning was mainstream available. So the solar heat gain was not as big of a deal because it could be dealt with HVAC. So if you're retrofitting these buildings built in the 60s, 70s, 80s, 90s, 2000s, it's probably a lot of glass. And if the glass wasn't set up for a low solar heat gain coefficient, SHGC, and you're making some upgrades to the building, it could be pretty important. That sun coming in, I want to reflect a lot of that back out. So if you're thinking about always do the lighting upgrades before you do the HVAC. The building envelope stuff, you may not ever be doing it. You may never be changing the windows. But if you're thinking about changing the windows, do it before you do the HVAC or at the same time you do the HVAC. So lighting first, then either building envelope or HVAC, depending on whether you were ever planning on upgrading the building envelope. Some buildings don't ever plan on doing that, but the lighting everybody's pretty much doing. All right, hopefully that covers us in terms of interaction. So that's probably the last non-HVAC thing I mentioned for the next 2 days. Will be all HVAC from this point forward. On existing HVAC systems, most of the issues, I don't want to say they're caused by the controls, especially the fact that in the 90s, that was my job, was programming building automation. So I'm kind of a controls defender. They're not caused by the controls, but they are typically caused by the controls getting messed up, meaning someone's touched something they shouldn't have touched. Somebody bastardized something. Somebody asked for the controls to do something that, yeah, the controls guy said, yeah, we can do that, but it was dumb, right? the controls guy can make the program do pretty much whatever you want. Whether that makes sense or not is another debate. So the main issues that we have on existing control systems, whether they are building automation systems or whether they're just simple thermostats, the building operator has not been trained effectively, or not even trained at all, which is super common, or trained, then he left, and a new person came in, and that person was never trained, right? Like I just mentioned, I did building automation system programming for about 10 years, and there was plenty of buildings that I would go back there 3 years later, and I'd be like, what the hell did you guys do? Why did you mess all this stuff up? And they'd be like, no one showed us how. And I'd be like, I trained you guys. And I'd be like, wait, I didn't train you. You weren't here, and you weren't here, and you. In fact, only one of you was the guy that was here when I first trained you guys 3 years ago. Everybody else is new, right? That's very common. So making things intuitive is helpful, and training people is very helpful, and retraining people is very helpful. A lot of times the system gets locked out by the operator. They log into the computer and they force something to do something it wasn't supposed to do. It's usually not because they're being dumb or being jerks. It's because something wasn't right in part of the building. They forced it to make the problem go away for that moment in time. And then either they didn't realize forcing that thing to happen caused other problems, or they completely forgot about it, right? And they never went back to fix it. And it doesn't have to even be a building automation thing. It could be a physical thing, right? There's plenty of times that I've gone to buildings and seen a 2x4 jammed up inside an outside air intake damper, propping it open. Well, how the hell is the control system supposed to shut the damper tonight? Or tomorrow night? Or for the next month? Oh, it's not, right? The scheduling is always messed up on all these buildings. There are so many buildings that are running 24/7, even though they have the ability to put a schedule in, because somebody didn't want to deal with it. They didn't want to go spend the effort to program it, especially on these small package systems like we're talking about today, because maybe you have 4 or 5 of these package systems, and maybe your company has 10 buildings like that, which means you now have 50 thermostats on the wall. And if you want to fix the scheduling, you got to go to 10 buildings and change 5 stats at each one, and maybe you just don't want to do that. Just a lot of effort, and you're just like, screw it. What do I care, right? There's a lot of people that don't put schedules in their home thermostat, and they pay that bill personally. So I told you how difficult it is to get somebody to schedule their building and schedule their thermostat. Economizer set points are always wrong, every time. Every job, they're always wrong. We'll go through that in detail, but for right now, just believe me that the economizers are set up wrong or disabled. For variable speed fans and variable speed pumps, the static pressure setting, which is how we control those types of variable devices, is set up wrong almost every time. They typically are set to provide way more pressure than is needed, because that's a safe answer, and make sure that, kind of like the scheduling, if I run it 24/7, the tenants aren't going to complain, right? If I put a schedule in there, maybe I was wrong and guessed that the time's wrong. Same thing happens with the static pressure on the variable speed fans and pumps. They put it at a higher pressure than they need, because the higher pressure means they're going to guarantee everybody gets enough airflow, but it could be wasteful compared to what the energy savings could have been. The lack of reset controls on boilers, supplier temperature sensors, chillers, all that stuff. Those devices typically have that reset built in, and it's frequently disabled by the operators. And then there's a lot of exhaust fans that run 24/7. There's more exhaust fans running 24/7 than there was HVAC and air handlers running 24/7. And there's a lot of those. So there's a lot of easy things we can do from the control standpoint to fix it. This study is getting kind of old. It's 10 years old now, 11 years old now. So I need to find a newer one to reference. But in any case, this one's from the Department of Energy, Lawrence Berkeley Labs. I don't think a lot has changed then in terms of the things that are wrong with most buildings, because most of the buildings we're talking about were built way before this study was done and haven't been fixed since. So they probably still have the same problems. So some of the top things that can be fixed on existing buildings: fixing the air side economizer, which we're going to talk about today; reducing equipment runtime, which is kind of a no-brainer, but people don't do it. Other ones that might apply to package systems like we're talking about today. My mouse froze up there. Repairing, replacing, calibrating sensors applies to package systems. Optimal start routines apply to package systems. VFDs can apply to package systems. So there are several of these on the list that we can do for the building types that we're talking about. A lot of what we're going to do is going to come from the control standpoint. All right, so these low cost, no cost things that we're talking about, testing everything, that's step one. Make sure things are working the way they're supposed to be working. If they're not, fix them to make them work the way they're supposed to work. Testing the economizers has to be part of the discussion. When someone's compressor breaks or when their gas heat breaks, it gets noticed pretty quickly on the next really hot or really cold day. If somebody's economizer breaks, it doesn't get noticed because the compressor takes over and solves the problem for you automatically, and hence you don't know your economizer is broke, but you're wasting hundreds, if not thousands of dollars in that process. So we'll talk about that today too. Calibrating sensors is pretty important. Some sensors are pretty good, like temperature sensors. Most of the HVAC temperature sensors are thermistors. Thermistors tend to not drift. They just kind of, either they're good or they're bad, so they're pretty easy to check. Enthalpy sensors, which we'll use with the economizer, and CO2 sensors, which we talked about last week for demand control ventilation, have historically drifted badly. The new ones are not as big of an issue. We switched to solid state on the enthalpy instead of the old horsehair, which is fantastic. Horsehair is not fantastic, solid state is. And on CO2 sensors, we have that automatic calibration routine that we talked about last week. So the reliability of both of those has dramatically improved in the past 10, 12 years. But you may have systems older than that where they have old sensors, and you may need to be looking at those things. I normally recommend all these things be calibrated twice a year. Ideally, most buildings would have somebody doing maintenance on all the systems 4 times a year. I realize people aren't always going to pay to do it that way, but ideally, every packaged rooftop you have or whatever it is on your building, someone mechanically inclined would be visiting that thing 4 times a year, every 3 months, and making sure everything's working correctly. Now, maybe you're not always working on the same thing. When I go do my maintenance check in December, maybe I'm not bothering to check the cooling cycle, right? And when I do my check in June, maybe I'm not bothering to check the heating cycle, right? But I'm doing different things on each of those. And on 2 of those 4 events, the annual events, I'd like you to check the sensor calibration. Somebody did type a question, and I got to expand the screen to see it. Let's see. Those are just comments. Someone asked if we can make the slides available. Yes, we can. If you send me a note afterwards, an email, I will reply back to you with the slides for anybody who wants them. All right, everybody thinks we're just kind of comments, and I agree with all the comments you guys put in. We'll keep moving, though. Cleaning coils. That sounds like an easy one, because it is an easy one. Now, nobody wants to do it, physically do it, because it's kind of a gross, not awesome job to do. But if you do it, there's a lot of benefits. For starters, if you clean the coil, there'll be less debris on the surface of the coil, and it's easier for air to move through the coil, and it will lower the pressure drop of the coil, which means it'll take less fan energy to operate. So on your indoor evaporator coil, by cleaning that coil, it'll cost you less blower energy. And the same thing on your outdoor condenser coil. All right, so you can save energy, fan energy, by having clean coils. You can also save compressor energy by having clean coils. Because if I have dirt on my coil, now instead of the refrigerant heating up the metal coil or cooling down the metal coil, and then that coil heating up or cooling down the air, now the refrigerant has to heat up the coil, the metal coil. Then the metal coil has to heat up or cool down the debris and dirt. Then the debris or dirt has to heat up and cool down the air. There's an extra step of process in there. Basically, the dirt acts like an insulator on the coil, and it makes it harder to cool or heat your building. So cleaning coils has an energy saving standpoint from the heating cooling standpoint and from the fan energy standpoint. Not to mention, just like we talked about last week when we talked about UV lights, if you have gross stuff growing on your coil, why would you not want to get rid of that? That stuff's going to flake off and go into the air. So if you have mold or bacteria growing on your coil, you'd like to get rid of it so it doesn't end up down in the occupied space where people are going to breathe it. So there's so many benefits to having these clean coils, and it's easy to do, but nobody likes to do it because it's gross, right? And if you're an HVAC guy on this call, and you're thinking like, well, I always tell the customers to clean the coil and they never want to pay to do that. It's super easy to do, especially residentially, but commercially it's still pretty easy to do. Just one time, you have to bring the decision maker up on the roof with you or under the air handler. Be like, hey, I want to show you some things on this unit, right? Just kind of explain a few things to you real quick. And you bring them up there, and one of the things you do is you open up that section and look at the evaporator coil, and you just point to it and say, dude, you ask the customer, like, what is that on the coil? Whatever that gross thing is on there. And then they say, how the hell would I know what that is? You're the HVAC expert. You tell me. And you're like, I don't know what it is either. It's gross. I have no idea what that is. I'm like, well, I don't know what it is. Like, well, we should probably get rid of it, right? And they're like, yeah, we should get rid of it. Like, I agree. Like, it doesn't belong there. There shouldn't be this weird slimy crap on the coil. We should definitely get rid of it. They're like, well, what is it? Is it bacteria? Is it mold? What is it? Like, I don't know what it is, but it's gross and it's ending up in your air. So irregardless of what it is, we should get rid of it. And they're standing there staring at it and they have to make a decision to get rid of it or not. And they're probably going to say, yes, get rid of it. Especially if they're the ones that work in that building. It's no different than when you go to the Jiffy Lube or whatever, right? The oil change place. and you have your oil change, right? It's whatever, it's $29.99 special for oil changes, and they come back to you and they show you all these other things. They're like, this is what your transmission fluid looks like, and they show it to you, and they show you a clean one. Say, this is what it should look like. It should be this red color, and yours is this black gunky color. You're like, well, that's not good. Like, I don't know anything about transmission fluid. I know that one's gross and that one's not. Would you like to change it, sir? And then either I say, yes, I would, or I say, nah, not this time, and I'm in a hurry. But then when I come back 3 months later and they tell me the same thing again, then I'm like, yeah, you know what? I said no last time. Let's just go ahead and get it done. Same thing's going to happen here. They might say no to cleaning the coil, and you're like, all right, fine, I'll leave it like that. And you leave it like that. And then 6 months later, you say it again, like, hey, by the way, the coil, that gross stuff on there, it's worse. And like, crap. All right, let's clean it this time. Let's get it done. Right? They'll eventually give in and want to clean it, unless they don't care about the building occupants at all, which is a whole other thing. Somebody asked, Mike asked, how often you should clean the coils. That's an excellent question, and there's no singular answer. It's going to be dependent on what's building up on the coil. So that's going to be dependent on a couple different factors. The main factors involved are going to be how good are your filters, how tight are your filters in the cabinet, meaning can airflow get around them, right? The less debris I allow to get to the coil, the less things could be stuck on there and growing on there. In order for me to have mold, for example, grow on my coil, if you guys were on last week, you probably heard me say this, but I need 3 different things to grow mold. I need to have mold spores. Well, they're everywhere. They're in the air. That's pretty easy to find those guys. There's millions of them everywhere. I need to have mold spores. I need to have moisture. Well, there's plenty of moisture on an evaporator coil because that's literally what his job is, to pull moisture out of the air and drain it away. So definitely have moisture available. And then I need a food source, something organic for the mold to eat. Well, a aluminum or copper material in my coil is not a food source. Mold will not eat metal. But if I have debris on there that came through the air, like pollen or whatever it was, that is organic. Now the mold can sit on there and eat that. So if I do a good job filtering, I don't have to clean my coil as much. And I don't want to say never, but possibly never. Not never, but not very frequently. But if you have crappy filters and all that crap's coming through, then you're probably going to have to clean it more often. So possibly you're having to clean your, say, your evaporator coil, I don't know, once every 2 years, unless you do a good job filtering, or you put a UV light like we talked about last week on there to keep the coil clean. The condenser coil, however, that's the coil on the outdoor airflow side of the equation. That doesn't have any major health risks associated with it being gross, although there could be stuff that flakes off in the air and goes like Legionella or something like that, but that's pretty rare. But that's going to reduce my heating and cooling capacity on my system. But it is going to get a lot dirtier because there's really no way to filter that one. So cleaning the coils on the condenser side is probably like an annual thing for most buildings. It might be less or more depending on what's in your area. If you got like a crap load of cottonwood trees in your area, okay, it's going to be a frequent cleaning scenario. But it kind of really depends on what's going on out there. Let's look at a couple other ones on the question list before we move on. Coil cleaning, cost versus benefit and payback. We talked about that a little bit last week. Let me see if I can jump over real quick to last week's slides. Oh, you know what? I think last week I might have showed you the slides, but in the interest of time, we might have kind of blew through them kind of quick. The payback scenario for the coil cleaning is going to be dependent upon your labor rates because it's mostly labor. The actual cleaning solution is minor. Okay, what happened to my mouse, dude? Okay, there. All right, let's skip along. For you guys that weren't on last week, or if I didn't have a lot of time to go through UV lights, let's just jump over to that one thing. We covered a lot of stuff last week, man. Okay, let me just pull this up. So we talked about coil cleaning as a function of the UV light discussion last week, right? So here was your efficiency losses based on how much debris you had built up on the coil. So if you just say you had, 0.01 inches of something on your coil, growing on your coil, that's a 10% efficiency loss in terms of your coil. Other things that we had talked about were pressure drop and airflow. So by keeping the coil clean, you can reduce the pressure drop through the coil, thereby increasing the airflow if it's a constant volume system. If it's a VAV system, you won't increase the airflow because the VAV tracks the airflow, but you'll decrease the energy because the VFD will slow down to match that up. Coil temperatures, this is showing an average of 3-degree improvement on coil temperature, meaning instead of you providing 58-degree cooling air, you can go back to providing 55-degree cooling air, which means I need less CFM, less airflow to get the job done. Similar thing on the wet bulb side. In terms of like actual projects, which I'm assuming is what Mike really wants to know, I have no idea. You'd have to look at the cost of labor in your area to figure out how much it's going to actually cost to clean the coil, and then after that you could calculate the paybacks. But if nothing else, on the indoor evaporator coil, just because you don't want gross stuff floating into the airstream, that alone should be enough reason to clean it, even if there was no energy savings. Energy savings is kind of a bonus on the indoor coil. A couple more just general comments. Thanks, Bob. All right, everything was kind of along the same lines there. All right, let's go back to where we were. Where were we? Oh, we were right there. Okay. All right, other things that we can do that are on the low cost side. Changing out motors to higher efficiency motors. A lot of systems, especially smaller package systems, have low efficiency, 60% efficient PSC, permanent split capacitor style motors. Putting in a more efficient motor, perhaps a NEMA premium efficiency motor or an ECM motor if it's a relatively small motor, upgrading those motors can save us a bunch of energy. It usually doesn't have a good payback to rip out a good motor, throw it away, and put in a more efficient one. However, once the motor does in fact fail or has been tested to be near failure and you have to replace it anyway, you may as well go ahead and put the high efficiency one in, because the difference in cost from regular efficiency to high efficiency motor is very minimal, right? The difference in cost from no new motor to any motor is pretty high, right? Relatively speaking. It's kind of like windows at your house. If you have reasonably decent double pane windows, it probably doesn't make any financial sense to rip out 30 windows, pay 30 grand to upgrade all the windows in order for you to save $50 on your utility bill. It'll take you decades to pay that back. But once your kid throws a baseball through the window and busts it, and now you have to buy a new window anyway, the cost to go from a regular double pane window to a double pane window that's argon filled with glazing on it or whatever is pretty minimal. I built my house. It's not a custom house or anything. It's just a regular, subdivision house. But we picked all the stuff that went in it in 2002, I think it was, and it came with the regular standard code compliant double pane windows, and it was $400 extra to go to the low E windows. Not $400 per window, just $400 for the whole house. And I was like, that's like a freaking no-brainer. Like, why would I not do that? And the lady that's helping us with everything, she's like, yeah, I don't know why people don't do that. Like, you're the first ones that ever even said yes to this. I'm like, are you serious? It's $400. I'm like, yeah, they'd rather spend it on countertops and doorknobs and stuff. I'm like, okay, well, I'm going to spend mine on windows because it's a lot easier for me to put new doorknobs in later than it is new windows. It's kind of like that, right? So I'm not going to just change the motor just because, but once it's dead or almost dead, put in the best one you can get your hands on. Generally speaking, doing good maintenance, i.e. cleaning coils and things like that, can give you a few percent, 5, 6, 7, 8, 10% in savings. It's going to vary by job, obviously, and the type of equipment you have. But for those of you that want just some kind of mental check figure, maybe that helps a little bit. The kind of systems we're dealing with today don't have guide vanes on the fans. Those are bigger systems, not package systems. But if they did, you want to get those out, put VFDs in their place. We'll talk about VFDs next week as well as part of staged air volume. And then we're not going to have any pumping systems on package systems typically. But if you did, there's stuff we can do there, primarily putting VFDs in as well. This study, this is from one of the utilities in Illinois, not my utility, one further south of me, but they just had it represented pretty well. So that's why I'm using it here, but it's pretty similar for most areas of the country on things that you can do that are realistic, which is not usually something that we associate with a utility study. No offense to my utility friends. Realistic to be able to implement. And there's 20 things on this list, and this was going to help them save. If you did all of those things, which you probably can't do them all at your building, right? It shows you how much energy would be saved for all of their customers in the area. Right, they're not going to do all of the customers. It's impossible. Not impossible, but it's unlikely. I'm just going to highlight some of the things that relate to HVAC. And then I'm only going to really talk about the ones that relate to package systems. So we already mentioned retro commissioning. Getting things working the way they're supposed to be working can have a measurable, perceivable, realistic savings. In this case, 7.3% savings for their customers. HVAC, fixing the economizers, 2.3% savings. Ventilation, there's two different ones on here, but I have 2 plus another 2 possible percent on being able to fix some of that stuff. These are super easy things that we can do. The other easy things on the list, if you haven't noticed, the other non-HVAC things are pretty much all lighting related. Improve the lighting, then the HVAC. That's like the moral of the story today, right? On the gas side, it's a very similar kind of discussion. Retro commissioning is way up there on the top of the list. It's one of the most effective things you can do to save energy in a building because it's not that expensive to have somebody go back and look at everything and then either fix it or recommend what be done to fix it, depending on what the complexity of fixing it involves. If you have a boiler system, which package systems don't typically do, adding hot water reset is super easy to do. It's a no-brainer. Energy management systems, which means building automation systems. A lot of the stuff on this list is boiler related on the gas side, but there's pretty easy stuff to do. How long should my equipment last? When do I need to get new equipment? I get this question, I'm not even kidding, 5 times a day. Hey, how long should my furnace last? Hey, how long should my chiller last? Hey, I bet I had a boiler for like 23 years. Is it time to get a new one? The simple answer is the age of the equipment should not dictate when you replace it, right? Just like the age of the car doesn't dictate when you replace it. I may have a car, like my car right now is 8 years old, right? I can keep driving it probably for another 5 years and not have anything. I've never had any major mechanical problem with the car. I know I just jinxed myself and it's not going to start when I leave tonight. But I've had other cars where after 4 years, I beat that thing to shit and it was done and I had to get a new vehicle, right? Like I remember being like 20 some years old and I blew the engine in my pickup truck, right? Well, the engine cost almost as much as the truck. Time to get a new car, right? So it's going to be the same thing with HVAC. If things are taken care of and well maintained and still operating at a decent efficiency, they can last a fairly long time. But if that's not the case, they'll last a short time. But for sake of discussion, I got to give you a number. So I'm going to use ASHRAE's data for life expectancy. Some of this data is pretty old and they haven't updated it. And that's just kind of the way it goes. I've been an ASHRAE member since, I don't know, 2001. If you don't know what ASHRAE is, American Society of Heating, Refrigeration, and Air Conditioning Engineers. That's why we call it ASHRAE, because nobody can say that whole name. But I've been a member since like 2001, and I didn't even know we had this chart. It's actually in our handbook, but the handbook is like 1,000 pages at this point. It's 4 books. But I originally got this chart from my buddy's wife. She's a commercial property evaluator, and I was asking her, I'm like, what do you guys like when you're evaluating these buildings? Like when you look at the HVAC, like what do you tell people? Like, do you tell them they still got life left? Like what are the rules of thumb? And she sent me over this chart, and I was like, this chart's from ASHRAE, and she's like, yeah, they have all kinds of good stuff. And I was like, damn it, I'm an ASHRAE member. I didn't even know it, right? So the property people are using this as well as the HVAC people. For today's purposes, let's look at some of the common things that we'd have for a package system, right? So a typical package system usually means a rooftop system, and we're typically talking about single zone. Average life expectancy is 15 years. That means somebody's going to have one that's 23 years old and it's still working well. And somebody else put theirs in the gutter at year 12 because they beat the hell out of it and didn't maintain it, right? But to give you a check figure, it's about 15 years. So if your system's around that age, that's going to affect my decisions. That doesn't mean I need to throw it away this year, but I either need to make plans to replace it, or if I'm not ready to do that, I at least need to know when something major goes wrong on this thing and I blow a compressor or whatever, do I really want to spend like $8 grand to replace the compressor, or do I want to just spend 20 grand to get a new unit in its entirety, right? Same thing with your car. I blew the engine. Do I want to spend X amount of $1,000 for a new engine, or I just want to get a new car and start over with a new warranty and all brand new things? So for rooftop air conditioning systems, 15 years is a pretty good check figure to have in your head. For you guys that have boilers out there, if you have like large cast iron boilers, which would be more likely to be found in small commercial buildings, getting like 30 years out of it is not abnormal at all. More commercial type boilers that are typically and historically steel, you're probably talking about 25 years for the boiler, right? So as those boilers get older, time to start looking at replacing those guys. Furnaces at your house or in your commercial building, furnaces are very common to see in a commercial building, or the gas furnace that is inside the rooftop air conditioner, right? That furnace, that gas-fired rooftop, 18 years is kind of the limit. And on a rooftop unit, it's probably going to be less. 18 years is more when I have indoor-based equipment. And at that point, you should be looking at getting a new rooftop. If you have unit heaters out in your warehouse or manufacturing plant, right, or just a general storage area in your small office building, look at those guys. For a gas unit heater, 13 years is the average, right? It's fairly short, right? So look at some of these things and kind of get an idea of when might I have to replace it. If I had to have a large centrifugal fan in my air handler, 25 years, right? For you guys that do chillers, 20, 23 years. Cooling towers, 20 years, right? So this is a good cheat sheet to have just to kind of know, like I said, sometimes it's longer, sometimes it's less, but this just gets you in the ballpark. Once you've done the easy stuff, right, the stuff we were talking about before, recommissioning systems, calibrating sensors, installing programmable thermostats, right? After that, you're going to start looking at things that are not easy, or maybe they're easy, but they cost money, things that are capital investments, right? So based on the last chart I showed you and some personal experience, this is what I would say. Your rooftop units and outdoor condensing units, if they're in that 10 to 15 year range, I would not be doing anything to improve them. Now, I'd still clean coils and stuff like that, but I mean, I'm not going to install extra controls on there. I'm not going to retrofit a VFD on a 15-year-old rooftop. I'm not going to put an economizer and demand control ventilation on a 15-year-old rooftop. I'm looking to get that thing off the roof at that point and get something else on there. So when you get to that age, I would only do the maintenance things and I wouldn't invest in anything new. And I would start my planning process for replacing the entire unit. So rooftops and condensing units at 10 to 15 year range. If I have control systems, by year 10, they're pretty obsolete. That industry changes so fast, and there's so many things that can save energy there that upgrading the controls every 10 years is pretty desirable. That next range of stuff, that 15 to 20 years, chillers I'm looking at in that range, cooling towers, the fans in my indoor air handlers, my boilers. Now, I just told you boilers sometimes last 30, 35, 40 years, but maybe around 15 or 20 years, I'm looking at a boiler that was 78% efficient, and now I can replace it with one that's 95% efficient. Just from an efficiency standpoint, I may pull the trigger on that project. So these are the kind of ages on when I want you to think about you should replace it instead of repairing it, if you will. And then if you have anything with constant volume pumping, get it out right away, right? Immediate replacement of that. And anything with an old pneumatic control system, even if for some reason you installed it last year, which wouldn't make any sense because these are old things, but if you did, you installed new ones, get it out immediately. There's nothing you can do with a pneumatic control system from an energy saving standpoint. It's completely useless in that regard. Get something in there that's automated. Oh, I didn't realize I didn't put the new screenshots in here. These are the old ones. All right, so don't quote me on the exact dollar amounts of these. Just know that there are rebates for these kinds of things. And before I share the slides with anybody, I'll put the new screenshots in. For some reason, I'd left the old ones in here. But it's basically the same thing, or at least similar. For air-cooled air conditioning systems or heat pumps, depending on the size of the system, the utility company incentives in the East Coast here, as part of the Mass Save program in Massachusetts, will pay you to upgrade your system. For you guys that are in Illinois, I mentioned that because that's where I'm from, so I know a bunch of coworkers around here. We have the same exact thing. And almost every utility has something like this, some with higher levels than others based on various reasons, but there should be something to do. Before you replace any mechanical equipment in your building, check your utility's website to see if there's something they can do to help you make the more efficient version of that thing cost effective. They typically will not pay you a rebate to do the legal code minimum thing because you got to do that anyway. They'll pay you to do something better than that. Utilities want to save energy. They want to keep things in check, and they're often mandated by state law to help you do that as well, right? So same thing will happen with various components on here, pumps, economizers. We'll talk about economizers in a minute. There's rebates for that kind of stuff. Heat pumps have rebates. These are more heat pump initiatives. All right, I want to show you this too. All right, so this is a software tool that I use. For you guys out in Massachusetts, when I come out there typically every year, every other year, and do classes with you guys in person, we install the software on your computers, we go through it and all that. Well, we can't really do that in the webinar version of this because installing software on 100 people's computers would seem like my nightmare. So if you need this software and you want to use it, it's a free software tool. It's available from whoever your carrier distributor is, which for you guys in Massachusetts, that would be DCNE. For my friends locally in Illinois, that would be us, TEC. If you're in a different state, I know there's some guys in different states, just ask me and I'll tell you who your carrier rep is. So with that being said, it's free because obviously everything in the software is going to illustrate to you their model numbers. But it can be used generically as well. In this example, I've picked carrier model numbers, but there's also drop downs on there for train. There's drop downs on there for generic unit, and you put in the efficiencies of the unit. But obviously their goal is to get you to like their stuff. But I'm just using it for the energy calc. So this is actually running on a larger calculation engine called HAP, Hourly Analysis Program, which is a pretty involved energy modeling program. So if I wanted to energy model a building and then put different systems in there to see how much energy those systems would save, HAP could do that. But it would take me a couple hours to build a basic building. And I don't want to do that because I'm lazy. If there's one thing you learn from me from these 3 weeks is know that I'm super lazy. So this is what I call a 5-minute tool because it only takes me 5 minutes to use it. And anything that takes more than 5 minutes probably means Ryan isn't going to use it. So I'm not saying I never use HAP. It's just I don't want to model a whole building just to find out if a rooftop improvement is going to help out. So this tool uses that calculation engine, but it's kind of an overlay on that tool. It's just kind of a new view that removes like 90% of the choices that you could have made. All right, you don't even have to model the building. So it's just a basic thing, and it can help me compare one thing to the other thing. That way I can decide, do I want to even present this to the end user or not? Now, if this is part of a much larger project, maybe I do this at the beginning to say, yeah, you guys should do DCV. Yeah, you guys should put an economizer in. Yeah, you guys should replace a rooftop unit. And then if they want to do a more detailed modeling to see how that works with all the other things they want to do, lighting improvements and whatever, okay, now we're in the HAP world. But as a quick example, this works just fine. Sorry. Excuse me. So I'll just give you kind of a quick tutorial. This is just a screenshot, but I'll give you a quick tutorial of what would happen. I can name the job, obviously. I can go into preferences and set some different stuff up like economizer set points and things like that, just some basic things. But for the most part, I'm not changing anything. I tell it where I'm at in the world because I want that weather data. In this case, I told it I was in Boston, so it's going to pull Boston weather data. I tell it what kind of building I have. It's pretty basic choices: office, school, retail, gymnasium, some basic stuff like that. Because that's going to give me an idea of how the building gets occupied, what kind of hours it's occupied, the pattern. If you remember the DCV from last week, we had that 2-hump profile. It'll pull that kind of stuff in. And then what my load is, my cooling load for the space. And then I can pick my energy prices. In this case, I just picked the generic EIA data for all of Massachusetts, just kind of a utility average provided by the federal government. You could also choose my own values, and then you could put in whatever values you want for kWh and for therms. But I just took the generic one for now. And what I chose to do in this case is model a code minimum brand new unit. So this is an IECC, International Energy Conservation Code 2018 version, which is our state code in Massachusetts and in Illinois and like 30 other states. I chose to put that in as my baseline, and then I'm putting in a proposed better than baseline unit. Now, that's what I'm doing for right now because I want to illustrate to you how much the code is going to improve stuff. But on a real job, I would probably put in what they have now and then what I'm proposing, right? Or I can have multiple columns. What do they have now? What's the code minimum? What am I proposing? But right now, I just want to do this one thing, right? Which is the worst. I'm going to replace the unit anyway. I've already decided to buy a new unit. What's the legal minimum thing I could buy versus what's a more efficient thing I could buy, right? So I plugged in that legal minimum option. Exact same size of units, exact same size of heating in the units, exact same horsepower of the fans. They're both 2-speed fans because that's code required now. They both have economizers. All I did was get slightly more efficient on the cooling side. And that, in this case, for me, is 11% improvement. And that's $174. It's not that exciting, but it's nice, right? A little bit improvement. This tool will also show me my savings over however many years I said. That is specified over here in the blue box. I have mine defaulted to 5 years because after that, people can't even comprehend what you're talking about. Like, I'm not going to be here that long. So over 5 years, it tells me how much I'm going to save, $872. Down below, it gives me a little bit more breakdown on where the savings is coming from. So $16 of savings is coming from the fan. That's not very much. $160 is coming from the cooling. That's pretty much all of it. And I'm actually being penalized $2 on the gas heating side. I don't know what that was coming off of specifically. Why did I get penalized on the gas heating side? Horsepower is the same on the fan. They're both 2-speed fans. Both have economizers. I'm not sure what that two was, what that rounding was, but it's essentially 0. But most of it's coming from the cooling side in this example. We'll revisit the software numerous times. As we talk about technology, I have a screenshot of the software to show you what that technology will do for us. Economizer, CO2, staged air volume fan, those kind of things. John asked if the tool can be used for a manufacturing facility. Yeah, it can. You can plug that in. You can plug in just about anything you want. There's all kinds of sample building types you can choose on here to get an idea of what's going to happen between option A and option B. All right. I don't know if you guys have seen this study before. This one's getting a little long in the tooth as well. This one's 15 years old, 16 years old. But this study was 500 rooftops at 180 different buildings. And they went and looked at these existing units to see what problems the units had, what was not working correctly, and categorized all of them into 5 different buckets. So 46% of the units had a refrigeration circuit problem. That typically means either there was a minor leak. If there's a major leak, somebody already fixed that. There's either a minor leak, or the unit was overcharged, or the unit was undercharged. So basically half of the time something's wrong. Economizers, 64% of the time something was jacked up. There's a more recent Honeywell study that has about 70%. By the way, Honeywell makes the vast majority of economizer controllers in the market, and their own study says 70% of them are jacked up in the field. But this one was 64% were jacked up. That means the economizers are either propped open, or the economizer is screwed shut, or the economizer has the wrong set points, or the actuator is turning but it's laying on the ground instead of being on the shaft. All kinds of things can go wrong with that, and we'll circle back to that in a little bit when we talk about economizers here. 42% of the time the system had too little or too much airflow. That's basically half. 58% of the time the thermostat was either wired wrong or configured wrong or not programmed. And only 27% of the time, that sounds bad, right? Where the sensors actually messed up. We always blame the sensors. Oh, maybe you got a bad sensor. Maybe you got a bad sensor. It's probably one of these human-based errors that caused the problem, not the sensor drifting out of calibration. Greg asks if that software tool will calculate heat pump efficiencies at different temperatures. It can be used for heat pumps. That's one of the options you can choose on here. I chose cooling with gas heat, but you could definitely choose heat pumps. I think I have some examples of that for next week. I don't know what you mean at different temperatures, though. The only temperatures that are involved in this discussion are going to be the economizer. Well, the only temperatures you can adjust are picking the weather data. You cannot actually on this tool go in and adjust any other temperatures. You can't adjust the economizer temperature. You can't adjust the weather temperature. You cannot adjust the indoor temperatures. On the full HAT modeling tool, you can adjust all of those things if you want to. But on this tool, it's assuming that on both options, the outdoor air would be the same. It's assuming that on both options, your thermostat set point would be the same. So it's removed all of the options like that so you can do things really fast. He's saying different heat pumps have different COP at colder temps. It does take that into account, but it's going to do it for those specific model numbers of heat pumps that are listed in here. So if you drop down a specific model number, Carrier or Bryant or a Train or whatever, a Lennox, whatever it was, it's going to have COP data loaded for that heat pump. What you cannot do on a tool like this is load in your own COP curves. You would need to leave this simplified 5-minute tool and go to a full modeling tool if you want to load your own curves for different COPs at different colder temperatures. This one's just going to pick the ones that are in there for those models. There's pros and cons to a simplified tool. 1, it's free. That's always a pro. 2, it's fast, right? But if you want to get more detailed, then you would need a more involved tool, which is readily available. It's just not easy and not fast. All right, I want to give you this checklist as well. Like I said, you guys can have access to these slides for those who want them. This checklist, this actually comes out of the Wisconsin, the original Wisconsin utility program for RTO, rooftop optimization. That program has since evolved into something else. But at that time when it came out, like, I don't know, 10, 12 years ago, we helped them, we meaning Energy Center of Wisconsin, which is now Slipstream, helped them put together some guidelines on on what things can be checked on the rooftop program. And then this is a screenshot of that, of kind of like the main points. So I use this with a lot of different customers because they like, I don't know what I should even be doing on there. I'm like, well, you've been in the industry for 12 years. How do you not know what to do? Like, can you just give me something? Sure, I'll give you this thing right here. So the first section on there is cleaning and maintenance. So cleaning and inspecting. It should really say inspect and clean, right? Because if you inspect it and there's nothing wrong, then there's no reason to clean it, right? But it's just a pet peeve of mine that it's worded that way. So the different things that you would want to inspect and or clean on part of this maintenance program. Things you would want to measure before you do that. So that's all another pet peeve of mine. The pre-measurements should happen before you do the cleaning. You should measure these things, do the cleaning, then measure them again. So it should be listed that way. The biggest thing to do is taking a temperature drop across the evaporator coil. This gives you an idea of how much cooling functionality you have, right? So if you have whatever 80-degree inlet temperature and you have 58 coming out, you're getting 22 degrees done on that air temperature, right? And what are you getting done after you cool it? So you can start seeing those things. So the temperature across the evaporator coil is an indicator to how much I've improved the cooling system by cleaning the coil. And then the blower amp draw is an indicator on a constant volume system, is an indicator of how much I've improved the airflow ability of that system. Right? And then I can do the same thing on the outdoor unit with that guy's amp draw. And then down at the bottom we have some airflow and refrigerant things. The refrigerant things are easy for HVAC techs to measure. The airflow, measured supply CFM and adjusted supply CFM. Believe it or not, CFM is cubic feet per minute of the air volume. Believe it or not, HVAC techs typically do not have tools to measure airflow. It seems like we should. It seems like that'd be an obvious thing, but we don't. Right? There's a whole separate trade, air balancers, or test and air balancers that measure that kind of stuff on projects for building checkout, commissioning, code compliance, those kind of things. Typically, it's not the HVAC guys doing it, which is very odd to me. That's kind of how it goes. So most of these forms we would get back on the utility program, those two weren't even filled out because nobody even had a way to measure them. But this just gives you some main things that you'd want to check. So you'll have this list. The refrigerant things, and there's even a note on here, there's no reason to start putting your gauges on the system. I know the first thing every tech does is put their gauge on the system. There's no reason to put your gauge on the system unless you suspect that something's wrong. So until you've measured the temperatures, there's no reason to put the gauges on. If you measure the temperatures and everything looks good, don't put the gauges on. Because every time you put the gauges on, A, you leak a little bit of refrigerant out on accident just by hooking them up. And B, you could allow a little bit of contaminant to get in. So there's no reason to get into the system if you don't have to. I'm going to give you guys this chart as well. This is what we call a scorecard. Our company's been using this. Hell, when I started in the 90s, we had a scorecard like this. In fact, this is probably the same scorecard. We just keep tweaking it with different refrigerants. But other than that, it works the same way. Normally, this is all on one side. There's red flags on the other side, but I've kind of broken it up into two different slides just for visual purposes today. But normally, it fits on an 8.5 by 11 sheet. And you put it on your clipboard and you walk through the building. So I'll walk through this here in a second. But the way this works is you look at each thing on the list and give the equipment a score, and then the lower your score is, the better your system is, and the higher the score, the worse it is. So it's like golf. You want a low score, and that's going to mean that your equipment's in good shape. Now, the points on here, everyone wants to debate that, right? So before you guys even start typing things in, like why is this worth more than that? Why is this worth more than that? The points on here are actually irrelevant. The purpose of having all the points on, and you can redo this and make it be whatever points you want. Like, oh, if the equipment is 0 to 5 years, it should be 0 points, not 1, Ryan. Okay, fine, make it 0. I don't care what you make it. The point of this is not to actually get the answer and to get the score. It seems like it would be, but that's not the point. The point of this is to make the building owner make a decision. Help them make a decision. So the real value of the chart comes in you discussing these things with the building owner, not in you getting the final score at the bottom. I want you to discuss each item with the building owner. Do not fill out this chart and hand it to them. That is worthless. You need to fill it out with them. Take the 3 minutes to do it together, right? So first one, age of equipment, right? How old is the equipment? You throw a score in here. Like, okay, they got a 12-year-old unit. You put 10 points in, and the guy's like, well, but I've done a really good job maintaining it. I think it's 12 years old, but it's really more like an 8-year-old unit. I should only get a 5 for that. Dude, if you want me to put a 5 down, I'll put a 5 down. Right? But we have quality of equipment condition over here. We're already going to adjust it over here. So we should put the real age in over here. No, dude, I really want to put a 5 in. Hey, put a 5 in. I don't care. It's whatever you want, Mr. Customer. This is you. I'm filling it out for you, right? So put in whatever the equipment age is here. The estimated cost of repair. The reason this is on here is because there are very few building owners that say, hey, come out and just look at my equipment. Just to kind of give me like a little glance over and tell me if it's in good shape. No one ever asks for that. If they do, great, but they're probably not going to do that. You're out there because something broke. They have a bad fan. They got a bad compressor. They got a bad inducer motor. Something's broke. That's why you're out there as an HVAC guy. So that's why we have this on here. There is a repair needed, and you're trying to choose, should we do this repair for $3,000 or should we replace the unit for $21,000 or whatever the costs are? So what's the cost of the repair? Put a score in. The more costly the repair, the more bad negative points you get. Right? Are the repairs under warranty? If they're under warranty, that's great, right? If they're not under warranty, bad points. What's the cooling efficiency of the system? Right? So you put that in there. The less efficient it is, down here in the bottom, the more bad points you get. The more efficient it is, the less bad points you get, right? So because the less efficient it is, that means it's costing me operating energy later on. What kind of refrigerant do you have? Do you have ones that are obsoleted or ones that are not obsoleted? By the way, we're going to have to update this chart because if you didn't know, package systems for the past 10, 15 years, and for my company since the 90s, we've used R410A. A lot of systems have R22, which is what you guys typically call Freon. Freon R22 is completely obsolete. That's completely off the market. You can't even buy equipment with that anymore. And R410 is on the chopping block next. So all the manufacturers are switching to a new refrigerant again to get lower ozone depletion potential. So we'll have to update this chart again. But for right now, do you have an old refrigerant, meaning R22 or older? And if you don't know which ones are which, over here, there's some notes over here. But the older your refrigerant is, the better, the worse. So the R22 on my old chart here, HCFC, that guy's 10 points down here. If you have a current refrigerant, meaning 410A, no negative points. On the heating side, and there was two columns for this, by the way, electric or heat pump heat, and then gas heat. So gas heat has the potential for more negative points because there's one extra thing involved. Well, lots of extra things, igniter, inducer, gas valve, burner assembly, etc. And if you have an electric-based heating system, you don't have any of those things to think about. So if you have an inefficient heating system, you could have more negative points. Then the big one, this is the most important one, equipment condition. The customer needs to say, is their equipment in good, average, fair, or poor condition? Nobody knows what those words mean. I don't know what those words mean. The dude who made the chart doesn't know what those words mean. You have to tell me, is your building, your equipment that we're talking about, this piece of equipment, is it good, average, fair, or poor? And I don't know what those things are, but the building owner has something in his mind or her mind on what they are. And they will immediately give you an answer. Oh yeah, dude, it's pretty good condition. Like, I feel pretty good about it, right? Or they'll say, dude, this thing is a beast. We got to fix it like every 2 years. It's definitely in the poor category, right? Just like if I ask you, any one of you guys about your car, your own car, is your car good, average, fair, or poor? Every one of you can give me an answer right now, but I have not defined to you mathematically what good, average, fair, or poor means. But you can give me an answer. You're like, yeah, it's average. It's pretty average. All right, 10 points. All right. So that one's pretty easy, but it's important. Why is it important? Because this tells you meaning the HVAC guy or you meaning the energy auditor, what the customer's perception of their equipment is and how ready they are going to be to replace it. If they say it's fair or poor, that gives you a lot of negative points. And it doesn't really matter at that point how old the unit is or how expensive their repair is. They're not happy with this thing. They probably want it to go away and get a new thing. And then how long do they expect to stay? You might as well just put 5 down because almost everybody tells me 2 to 5 years, 2 to 5 years, 2 to 5 years. It's like the most common answer that I get when I ask this question, right? But the longer you plan on staying, the more sense it's going to make to invest in the equipment because you're going to be there to benefit from it. If you're leaving this year, dude, just skip this whole chart and just repair it. Like, move on. It'll be somebody else's problem next year, right? Then you add up all the points and you get a score. Once again, I don't really care what the answer is. I just want the customer, the end user, to think about things. So I either have a repair question or a repair score or a replace score. If the score is really high, dude, don't spend any money to fix this unit. This unit's a lemon, excuse me. Let's just get rid of that thing, right? It's done. Or if it's a low score, it's like, well, you got a lot of life left in this unit. You're pretty happy with it. Let's just go ahead and fix the one thing that's broken and move on. And then, quite honestly, most of the time, the answer ends up in the middle, which is fine because, once again, I wanted them to go through the process so they can decide how they feel about the equipment, and then they can make a decision. Honestly, I don't care if they repair it or replace it. I just want them to think it through. The other side of this scorecard would have these red flags on it. and they're broken up into different categories: airflow, noise, indoor air quality, etc. All right, and you just say yes or no. So what you cannot do is ask the customer, hey, so you did all this with them, and then you say, well, do you have any problems with the unit? And they'll be like, well, we had to replace that gas valve like 2 years ago, but other than that, well, do you have any problems in the building, like comfort-wise? No, everything's good. They will always say, no, everything's good. Same at a house. You ask any homeowner, hey, is there any comfort problems in the house? No, it's been pretty good. And then if you say something different, like, which room in the house is the coldest? Oh, dude, it's Billy's room. It's at the end of the house over there. His room is always freezing. But wait a minute, dude, you just told me there's no comfort problems. They've gotten so used to it, they just think that's normal, and they don't identify it as a problem. You have to be very specific. So in the case of the commercial building, you have to say, are there any rooms that are too hot in the summer? Oh, yeah, president's office. Dude, that place is smoking hot. As soon as the sun comes in on the glass, he's always complaining. Well, hell, he's the president of the company. Let's get that fixed, right? Are any rooms too cold? Do you have any rooms with airflow issues? Oh, yeah, in the break room, like it comes out of the vent like a trickle. Like it's just barely wimpy coming out, right? Is there any weird noises or anything? Oh, yeah, there's a whistling noise in Betsy's office. They will tell you everything if you ask them very specific questions. Why do you want them to tell you everything? You tell them everything, now you have the opportunity to go fix it as part of this project. And part of this project, I know we're talking today about replacing for energy efficiency, but if I can fix your comfort problem and your airflow problem at the same time I get you something more efficient, why not, right? Do it all at once. Plus, it's probably going to take that to get them to make a decision. They're always going to lean towards the cheaper thing, which means replace it. But if they end up in this questionable area, or even in the replaced area, they end up in those areas, and you can also point out to them how crappy their system is and what you can do to fix those things. Now all of a sudden it's like, yeah, well, if I can fix the president's office being hot and we save some energy at the same time, maybe I should look at replacing this thing with a more efficient, better controlled unit. All right. Have you guys had any questions? Type them in. We got a couple more slides, and then we're going to get into a break, and then go into some specific technologies. You probably have seen this slide before or one like it. This is showing you a map of all of the current energy codes that we have throughout the country. Wait a minute, this might be the old map too. This is a little bit older. I need to put a new map in here, I think, because it says as of November 2018. I need to get a new screenshot from VCAP. I put a new one in. Let's just see for argument's sake, just for the heck of it, give you the current map right now. A VCAP, Energy Codes Assistant Project. Okay, now I remember why I didn't put the new map in, because their website's down. Okay, well, that explains that. All right. I forgot why I didn't put a new map in. All right, I will put a new map in whenever the website's back up. I tried a couple days ago and it was down too, so I don't know what's going on there. Maybe their funding ran out. In any case, Massachusetts, where most of you guys are from, would now move into this light blue color, just like Nevada and California, because we're on the 2018 IECC, which is ASHRAE 2016. Same with Illinois. Would bump up onto there as well. And a lot of other states would trend along with that because, believe it or not, in the past 2 years, a lot of the dark blue states have moved to the light blue color. Everything else in this slide deck will be based on the 2018 code. I just need to update this particular one and this particular one. The energy codes have been getting more efficient over time. Green is commercial code, right? We started out in the 1970s with ASHRAE standard 90.1. Literally, the federal government came to ASHRAE and said, help us make a standard. This was during the oil embargo and all that stuff that keeps buildings more efficient. So they made a standard and started asking buildings to build to that, of which almost none of them did. Because by then, the oil embargo was over and moved on, and energy was cheap again in the 80s, so no one cared. But over time, things kind of kicked back in, and now the code gets stricter and stricter, and every 3 years it gets improved. This was the big leap to go from 2007 to 2010, and if we did it again, there'd be another little leap down here to get us even more efficient. Our current code for the vast majority of states, including the majority of you guys on here. Oh, Chris sent in a better link. See if I can copy that. Okay, instead of the BCAP one, he sent the energy codes one. Let me see if we pull that up real quick. The BCAP one is all crippled up. Thank you, Chris. Okay. I don't know if this is current either. Let's see. Okay, it is. Let me get rid of this thing out of my view. All right, so we'll look at this one for purposes of discussion. Thank you, Chris. So 90.1 2016 is in this dark green. Yeah, this is old too, though, because Illinois, we switched a year and a half ago, so we should be in dark green as well. So this is not updated either, but it's slightly more updated than the one I showed you before. That's okay. We tried. All right, so we're almost all of us on the call are on 2018 code. So first question I often get is, does it apply to me? Like, isn't that only for a new construction thing? No, it's not only for new construction. It does apply to existing buildings, for sure, as did 2015, by the way. It's not a new advent here. And if you read some of the language, then 2018 now has a separate section for existing buildings, and it says you don't have to do some of the things in the code. And because of that, people will come to me and say, well, I don't have to comply with the code because I'm an existing building. No, you have to comply with the existing building section of the code instead of the new construction section. But when you go read the existing building section, at least for the things that relate to HVAC, guess what it happens to say? Any new mechanical systems you put in, meaning a new rooftop or a new air conditioner or new ductwork or whatever, that are part of an addition, you have to comply with section C403. Guess what C403 is? It's the entire mechanical section related to new construction. So you have to do it, right? And then if you have an alteration, not an addition to the building, but an alteration, you got to comply with section C403, right? And if you make repairs or replacement of widgets, components, guess what you have to do? Go and comply with the mechanical section. So the exceptions that are in there, yeah, there's ones in there for existing buildings, but not really for HVAC. You got to do all the HVAC stuff. So new construction, existing buildings, it's all the same. You have three ways that you're allowed to comply with the code. You can either throw the code book in the trash and instead follow ASHRAE 90.1 2016 version in its entirety, or you can follow the international code in its entirety, one or the other. What you cannot do is cherry pick some things from one and cherry pick things from the other. You either go into this book or you go into that book. And if you follow 90.1, then IECC says that's good enough. You followed enough things that we're good with that. All right. If you didn't know, 90.1 comes out every 3 years. 18 months after that, IECC comes out, and it's almost a cut and paste. Like, seriously, it's that close. Like 95% of the stuff is exactly the same. The tables are all the same. The values are all the same. And then they just tweak a few things. The 90.1 is ASHRAE. That's the engineers writing it. IECC is the code inspectors writing it. So they changed some of the things because some of the things that ASHRAE asked for, they felt were difficult from a code enforcement standpoint, so they didn't want to do it. That's really what it is. So you can either do 90.1 or IECC. If you're doing IECC, you can either follow number 2 or number 3. So number 3 I'll talk about first. That means you would energy model the building as if you built it to code, then energy model the building the way you want to build it, and if you beat that by 15%, it's called code compliant. So you can trade things off and say, you know what, I don't want to get windows that are that good. I want to get shittier windows. Sorry for my language. I want to get crappier windows. Okay, well, you better get a better chiller, right? You got to trade things off. Number 2 is what we're going to use today. That's the prescriptive method. So for small systems and package systems like we're dealing with, there typically isn't going to be any energy modeling. They're going to replace 3 rooftops, and they're just going to pull them off and put the new ones on. So I'm going to follow number 2, which is the prescriptive method. It says, do this, 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 and this, and you're good. Just follow the list, right? That's what we're going to do for today's purposes. So the effects that energy code is going to have on my equipment, it's going to affect my size. We're going to talk about all these individually, but it's going to affect the size of my equipment. It's going to affect the efficiency of both my cooling and my heating. It's going to determine what kind of thermostats I have to use and how I have to set my thermostats up. It's going to force me into economizers and some unique control requirements of the economizer. It might force me into demand ventilation, ERVs, VFDs on my fans. I have to do load calcs. I got to seal ducts. There's going to be a lot of things that it forces me to do here. And we're going to talk about some of those things as we dive into each one of these technologies. We are at 10:36 Eastern, 9:36 Central. It is a good time to take a break. Let's come back at 45. So we'll come back at 10:45 Eastern, 9:45 Central. So you guys can all refill the coffee and do all of those wonderful things. All right, hopefully everybody is ready to resume. Keep typing questions in, and we'll keep trying to answer them. I don't know who we is. I guess I'll keep trying to answer them. There's nobody else here. So as part of that code, we're looking at sizing and efficiency of these package systems. If you were not aware of it, most systems in the United States are oversized, and they are grossly oversized. This example here is talking about fan systems in the U.S. that are oversized on average by 60%. So I'm sure there's somewhere out there where there's a fan that's like perfectly sized, but there's a bunch of them out there that are probably 100% oversized, and it's pretty dramatic. Same thing with chillers, same thing with boilers, rooftop units, fan coils, residential furnaces. Like literally 100% of systems are oversized. I could do literally a whole hour-long webinar on oversizing. In fact, I have done that before, so if you're bored one day and you want a recording on a 1-hour webinar of me bitching about oversizing, I probably have that somewhere. In fact, in general, almost everything we're talking about probably exists somewhere else as a 1-hour webinar, because I've been recording these things for like 12 years. So I'm sure I have it somewhere, or I have it as something as a short video. Long story short, if you're looking for something that I talked about, say, hey, I wish I could learn a little bit more about blah, 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 just send me a note. I may have a resource that either I made or someone else made that I can send to you. I may not, but I may. So ask me and I'll send you whatever I can dig up. We spend very little time at full load. So even if we did size something 100% perfectly, which no one does, everyone oversizes, but if we did, there's very little times of the year we actually would need it to operate that way. So what I need everyone to stop doing, literally everyone, is to stop adding safety factors. Don't add safety factors. Just size it correctly, trust your calculations, and move on. Don't add safety factors. Or at least at a minimum, don't add safety factors on your load calculation software inputs. Inputs meaning like, what kind of windows do you have? What kind of insulation do you have? You know, all those kind of questions when you're answering them on your software. If you guess, and you guess conservatively, i.e. adding safety factors on all of your inputs, that really magnifies the final answer. And then most of you guys take the final answer and then you round up anyway. You add another safety factor. So at least put very pure inputs in and guess very aggressively if you have to guess. And then at the end, if you need to add a safety factor or you need to round up to the next whole size, that's one thing. But you guys, I'm saying you guys generically, you're putting safety factors on the inputs and on the outputs, and it's causing a mess, meaning a lot of stuff is like double sized. For example, where I live in Aurora, which is like an hour west of Chicago, our design temp for heating is like -5 degrees. This year we got down to -18, I think it was. A couple years ago on that polar vortex year, we got down to -26. Everyone's furnace and boiler kept up. Everyone's. Anyone that said no when I asked them more questions is because their furnace broke. But no one had a furnace that wasn't broke and still couldn't handle a -26 day when it was only supposed to handle a -5 day. So everybody's stuff's oversized badly. On the cooling side, it's even more important than on furnaces and boilers. If you oversize the cooling, it will be a dehumidification problem for the building. Your system only dehumidifies when the compressor is running. It sends cold refrigerant to the indoor evaporator coil. That coil lowers the temperature of the air coming through it until it gets down to the dew point of the air. Then it can start pouring moisture out. It takes a few minutes to do that. It has to run 4, 5, 6 minutes before it hits the dew point and hence dehumidifies. If your system's oversized, your thermostat asks for cooling. It provides a lot of cooling because it's oversized. It satisfies the thermostat very quickly, which sounds like a good thing, but it's actually horrible because I didn't run very long, which means I never got down to the point of dehumidifying the air. I need the system to run for a long time. I need every time the cooling kicks on for it to run 15, 20, 25 minutes at a crack, preferably longer. I finally have my system in my house kind of optimized, and it'll run in the summertime 4, 5, 6 hours at a crack without even cycling off once. I've sized it smaller, not too small, but smaller. And I have it a lot of stages so it can just continuously run without ever shutting off, and it's wonderful. And that's what we need to get to with all these other commercial systems as well. You'll have less temperature swings and comfort complaints if you can size the equipment smaller. I used to say downsize equipment, but now I call it right sizing because when I say downsizing, people would freak out. I don't want you to size it below what it's supposed to be. I want you just to finally do it for once the way it's supposed to be instead of oversizing it. So less temperature swings, less wear and tear on the equipment, less on and off cycling. It costs less to buy smaller equipment. It saves kilowatt hours and it saves demand charges. Like everything's a positive. There's no negative to sizing it smaller. Not smaller than what you need, smaller than what you think you need. In regards to demand charges we talked about earlier, just to give you an example on here, if I was to put in a 10-ton unit, so let's just look out over here. Let's say I looked at A12 on here, 10 tons. It is 10.6 kW is my draw when that thing's on. If I was to replace that with a 7.5 ton, it is 8 kW draw. So it goes from 10.6 to 8, 2.6 kW less. Doesn't sound like a lot. If I'm doing that on all my equipment, it starts becoming a cumulative effect, and it can affect the demand charges on my building. Load calcs are not optional. You're required to do these by energy code. So every one of you that's on this call, I believe when I looked at the list, everybody's from a state that has an energy code. Everybody has to do this. It's not an optional thing. Every time you put in a new piece of equipment, you have to do a proper load calculation. The code dictates the indoor temperatures. At most, you can design it to heat for 72. You can do less. You can design it to only heat your building to 70, but at most 72. And cooling, the lowest temperature you're allowed to decide the cooling for by law is 75 degrees. There is no code in any state that allows you to design cooling to go below 75 degrees. Every single one of you operates your cooling system below 75 degrees. Maybe not every one of you. Maybe there's somebody out there who doesn't. I don't at my house. Mine's at 70. Like I said, I've done a lot of sizing things at my house differently. Everybody else mine's at 77. The code is 75. 77 would be allowed. Anything below 75 is not. So when your customer asks you to design the building to be cooled down to 72 or 68 or something like that, don't do it. When you do that, you oversize it more, which means they have to lower the set point more to get it to run long enough to dehumidify. It's a self-fulfilling prophecy. The more oversized the equipment is, the lower the cooling set point you have to get it to run. So if you size it smaller, it'll run long cycles at the 75 degrees and hence dehumidify. And if I can dehumidify well, all of a sudden 75 is very comfortable. Like I just told you, I keep my house at 77. I can't keep it at 75. It's too cold. Why would 75 be too cold, Ryan? That sounds kind of ridiculous, dude. And it's not because like my family's a bunch of wimps that like it to be warm. I mean, I can't get my kids to put pants on and sweatshirts on in the winter. Like they go out in shorts and a t-shirt all the time. My wife wears flip-flops outside in the winter, right? So it's not like they like it warm or something like that. It's just that I dehumidify so well at my house because of all the things I've done to it that it's super dry at 75, right? It's like 30% humidity in the summer, whereas your house is probably 65. So it's so dry that 75 feels cool. So I got to keep it a little bit warmer, 77, which is great because it saves energy. In any case, this is dictated by code. You're not allowed to design cooling below 75. You're required to do the sizing. It's not optional. Typically, we're going to look at ASHRAE data for commercial buildings to do the weather data. So what temps do you guys design for? Most of you guys are from Massachusetts, so we'll use Boston as our example. This is out of the ASHRAE handbook. You don't have to use ASHRAE. I mean, you're going to, but you don't have to. So it doesn't say in here like thou shall use ASHRAE. You have to use ASHRAE standard of 183 or an approved equivalent. What's an approved equivalent? Well, if you don't want to use the ASHRAE data, I'm sure your authority having jurisdiction for code will allow you to use other weather data. What's other weather data? Maybe you get it from, what's the other one? I can't think of it, the oceanic people. I don't know. There's somebody else that has weather data. You can get it from an entity like that. Is it NIOSH? I can't remember what it is. You can get their weather data and you can use that if you wanted to, right? That would be fine. But what you can't do is say, well, my grandpa has a thermometer and a yellow legal pad. There, everyone's putting it in NOAA. NOAA. Sorry about that. Yeah, NIOSH is like the air quality people. Any case, so NOAA, thank you guys. Thanks, Nicole and Lauren. So you can get it from there and use that, and you probably get your authority to approve that. But they're not going to approve like you having your own weather records on a clipboard. That's not going to work. So if I look at ASHRAE, which is what almost everybody uses, I'm looking at Boston for our example here in yellow. There are two heating numbers, 99.6 and 99. The code doesn't say which one you have to use, right? It just says you have to use ASHRAE, right? So I can use either one. What 99 means is 99% of the year it's going to be warmer than that number, meaning 1% of the time it's less. 99.6 means 0.4% of the time it's below that number. So 0.4% of an average year on a 30-year rolling average, it's below 8 degrees in Boston. Does it ever get down to -3? Sure, it gets down to -3 once in a while, but that's not a normal scenario, and hence I'm not going to design for that. I'm going to design for this statistical worst time. So 8 degrees is my heating design here. I can be less conservative, go to 13, but nobody ever does that. For cooling, I actually get 3 columns. And it works the same way, and it's just worded weirdly. So the 99% calm for heating is the same as the 1% calm for cooling. It's just a bell curve, and they're telling you you're on the 1% side of the curve or you're on the 99% side of the curve, but it means the same thing, right? So this means 1% of the time it's above 87.6 degrees in Boston on a 30-year average. 0.4% of the time it's above 90.6. There's also a 2% calm. I've never seen anybody use that, so I don't even bother highlighting it. Most people will use the 0.4. So in Boston, I just should design for 8 degrees in the winter and 90 or 91 degrees in the summer. Will it ever be 96 in Boston? Yeah, sure, it'll be 96. But that's not what I'm designing for. That'll happen, but it's a freak occurrence. And it's brief. It's not going to be all night long, right? And if it is, for the one time it happens every 80 years, fine. I'd rather be awesome for the entire year and have one day where it's not awesome, if I had to choose. Efficiency of equipment. The kind of equipment we're mainly dealing with right now is rooftop units. That's the bulk of packaged equipment. It could be a split system. Rooftop means everything is on the roof in one box. Or that box could be on the ground next to the building. But in either case, it's all outside in one box. It has my fan. It has my indoor evaporator coil. It has my outdoor condenser coil. It has my outdoor fan. And it has my gas heating section or electric heating section if you choose to do it that way. All in one box. So that's a packaged rooftop unit. A packaged split system would put those things into two pieces. It'd be more like your house. You'd have a condenser coil and a compressor and a condenser fan outside, and inside you'd have an indoor fan, evaporator coil, and a gas heater. But for these type of systems, if the system is less than 65,000 BTUs, so 5 tons of cooling and less, the system gets rated as a residential system, even though we know you're putting it into a commercial building. That's just the way they do it. These ratings are all from AHRI, American Heating Refrigeration Institute. It's ARI and Gamma merged together like 15 years ago. It's basically a collection of all of the manufacturers as well as some other stakeholders that get together and write the standards on how stuff should be tested. And the reason for that is to make it so I can compare manufacturer A to manufacturer B in a relatively fair fashion. In any case, for small stuff, it gets to use the residential standard, which means the main rating for cooling would be SEER, just like it is for your house. And for the gas heating section, it would be AFUE, Annual Fuel Utilization Efficiency in terms of percent. SEER is Seasonal Energy Efficiency Ratio. When we get to the bigger stuff, which would be over 5 tons, then what I have for cooling is 2 ratings. Well, actually for residential, I have EER and SEER also. Everybody just ignores EER though. But for commercial, I still have 2 ratings, EER and IEER. EER is Energy Efficiency Ratio. That means I run this system on a 95-degree day to make 75-degree indoor. I run it at maximum capacity. I let it get stable. Then I measure how efficient it is. Peak full load efficiency. SEER or IER are both part load efficiency things. They have a full load portion to them, but they are heavy on the part load. And I'll show you how IER works in a minute. But it's more focused on part load. Part load is significantly more important because full load only happens on the hottest day of the year, which is 0.4% of the time. Unless I've oversized it, then it's never. So IER is more important. It used to be that we only had EER for commercial stuff, and then maybe like, I don't know, 8 or 10 years ago, we added IER. And now we're almost ignore EER, and we're almost fully focused on IER, and I'll explain that too. Oh, Chris typed something in. Let me expand it and see what he said. All Chris's notes are always long, apparently, so I have to expand my screen very large. I can even get it to fit in here. Okay. It can be confusing. Okay, he's talking about something else that he and I were discussing. Separate sidebar. Okay. For gas heating for rooftops, we use thermal efficiency. Thermal efficiency is kind of like the old school EER I was just explaining, but it's on the heating side. It means I'm going to run this system at maximum capacity, let everything settle out and equalize, and then measure how efficient it is. Whereas AFUE on the residential side takes into account part load. Commercially, we have no part load metrics on the heating side, on gas heating, only on the cooling side, and the cooling thing's relatively new. So why is part load important? This is why part load is important. EER is for a 95-degree day, which statistically doesn't happen in Boston. I mean, it might happen on occasion, but statistically, no. I have almost no hours there. I have very few hours in the 90s for that matter, right? Whereas I'd love to be awesome and efficient at everything in this blue box. If I can get all those cooling hours right, that's a couple thousand hours of operation. Whereas if I get things really awesome and efficient and the 90 degrees, it's only tens of hours of operation a year. It's not super exciting. So I want to be more efficient here. It's a better point for me to care about energy efficiency as well as helping out that dehumidification we talked about. Here's how we calculate IEER for those that care. We actually measure 4 different operating points. There's one at 100% loaded, one at 75, one at 50, and one at 25% capacity, essentially. And then what we do is take those efficiency numbers and we give 2% weighting to the full load number. We give 62% rating to the 75% number. We give 24% to the 50, and we give 12% weighting to the 25. The reason we give less over here is because we're probably going to be in an economizer mode for a lot of these systems, and we'll talk about economizers in a little bit. That's why we don't give much weighting and much thought to that. So we heavily load this middle section over here. We're basically saying full load doesn't matter because it hardly ever happens. Very low load doesn't matter because it's probably going to get free cooling from the economizer. So let's get efficient in this middle range here. Right? That's just explaining kind of what that is. Not only do the energy codes now include IER, but the Department of Energy metrics no longer have any EER at all. They don't even look at full load in any way whatsoever. It's all part load efficiency because full load is old and irrelevant. When I look at the energy code, which we're required to comply with, obviously, for both new construction as well as replacement units, if I look at the small stuff, 5 tons and less for packaged systems, I need to be 14 SEER. Package meaning like a rooftop. If I have a split system, 2 pieces, 1 indoor, 1 outdoor, I only need to be 13 SEER. But 14 SEER for the packaged systems. If I go to the big stuff, they need to look and see like how big is big in this discussion. So 65 to 135,000 BTUs. And then if I have electric heat or I have all other heat types, all other means gas heat or hydronic heat. If it's a heat pump, there's actually a separate table, which is a separate discussion for another day. All right, but here, if I look at gas heat, which is most rooftops, I need to be 11 full load, 12.6 IER part load. And as it goes up in sizes, it becomes less and less difficult for the manufacturer to hit that because the manufacturing volume is pretty low on these guys down here. And I'm pretty restricted from a size standpoint to get more surface area. But small stuff is getting more and more and more efficient. Department of Energy also has its own minimums, so that's code minimums. Then the Department of Energy establishes minimums. Code minimums are policed at the local level by your code official. The DOE minimums are policed at the national level and at the manufacturer level. They're not allowed to build anything less than this. So a manufacturer, if they had built something less than this in 2017 and your distributor still had it laying around in inventory and it still complied with your local code, you could put it in, right? But they can't build anymore after X amount of date. In this case, 3 years ago, they had to build everything this good or better. If I go back and look at that little software tool that I had before, this is going from an entry-level unit. Oh, we already did that earlier. Okay, we skip that. If I look at all these guys side by side, so I got some examples here: 5 ton, 10 ton, 15 ton. And if you were to comply with Energy Star, how good would you be? If you complied with the old energy code we had up until 2 years ago, how good would you have to be? If you complied with Department of Energy, or if you comply with some of the various utility rebates, kind of tearing you along, seeing how you're tweaking along, getting better and better and better. And like I said before, all the utilities make you have more efficient systems than the code minimums in order to comply. If you have higher efficiency units, you'll have lower demand charges typically. So for example here, I'm showing you a standard efficiency unit in this table over here, high efficiency over here on the right. If I take an example, let's say a proverbial 10-ton unit. Let's say I take a 10-ton 2-stage unit. It's 10.3 kW, which will go into my demand charge. If I take a 2-stage 10-ton unit that's more efficient, it's 10. So it goes from 10.3 to 10. Is it a huge demand reduction? No, it's 0.3. But it still helps a little bit, especially when I have multiple pieces of equipment. If I go from this mid-efficiency unit up to an ultra-efficient unit, and I pick a 10-ton, it goes down to 8.9. So 10.3, 10 kW, 8.9 kW. So the more efficient my unit gets, typically the lower the demand charges will also be. That's not the reason why I'm doing it. I'm probably doing it for the kWh savings, but the kW savings doesn't hurt. All right, let's start diving into some specific technologies. We're going to have programmable thermostats here. We'll do that one pretty quick because that's pretty well known. Then we'll spend the rest of our time today on economizers. And then we'll pick up next week with staged air volume and VFDs, heat pumps, VRF, etc. So programmable thermostats, this is pretty much a no-brainer. Stop running stuff 24/7. If you run it all night long when you're not there, it's a waste of energy. We want you to relax your set points at nighttime or whenever when people are not there. My normal recommendation is get at least a 5-degree setback. So if you normally heat your building to 70, let it set back to at least 65 at night. You might be able to go lower. It'll depend on your building and how fast it can recover the next morning. But 5 degrees is a pretty good starting point for trying it out. On the cooling side, if you have a 75-degree set point, let it relax up to 80 degrees at night as an initial step point, initial trial run. You might be able to go a little bit more. And then you need about 6 hours for this to start being effective. Will it save energy if you only do it for 2 hours? Sure. It's just at some point, the effort for me to program these things compared to the amount of money I'm going to save, to let it go in the setback for 2 hours is kind of wimpy. 6 hours is kind of the minimum. Most buildings can do more. If your building's occupied from 7 a.m. to 5 p.m., what is that, 10 hours? That gives you 14 hours of setback you can do. So most buildings can do way more than this. This is kind of like the minimum effort to put in here. On average, thermostats can save like 25% of your energy consumption for heating and cooling, which can be quite substantial. So it is pretty easy because programmable thermostats are inexpensive, so it's easy to use. The problem is people don't program them. Now this data I'm showing you is residential because I don't have good commercial data, but the behavior I have found commercially to be even worse than residentially. Because residentially, it's your own house, it's your own bill, so maybe you're likely to program your stat. Commercially, the person in charge of the stat may not be the person paying the bill, so they may not care at all. And it's just easier not to put any program in. Even though it wastes money, it's just easier. So residentially, 89% of the customers don't program their programmable stat. That's a lot of people, and that's pretty horrible. So it's pretty easy to go into an existing building as part of your retro commissioning process and reprogram the stats correctly and save people a bunch of energy, tons of energy. I manage all the thermostats at our company now. We have like 30 different buildings, and I'm not part of the maintenance team. I'm not involved in the building management team or anything like that. I just got sick of them not being programmed at buildings. So as I would go to buildings, I have classrooms at all these different buildings. As I go to the buildings and I'm doing something in my classroom, I always look at the stat. It's always all jacked up. So I just started ripping them off the wall and putting Ecobees on the wall, which is a programmable smart stat I can work on remotely, and locking them out and then managing them remotely. I let the people at the building have a little bit of leeway up and down because remember my early slide? I don't want the people to be uncomfortable because then they complain, right? And then they're spending time complaining instead of working. So they have to have some controllability, but I don't let them get in and mess with the scheduling. There's no reason they need to change the set points in the middle of the night. They're not there, so that doesn't affect them. And I manage it all that way now. Not my job. Just got sick of people doing it wrong. So now I do it remotely. They're very easy to retrofit programmable stats. It's not a challenge at all. The biggest issue is sometimes you might need a couple extra wires, like a common wire, but we have ways around that. One of the features you may want to utilize is adaptive intelligent recovery. It's also called smart recovery. It's called optimal start. There's different names for it from different manufacturers. What it means is it looks at the previous run history for the past couple days and decides how long did it take to heat or cool this building up the last couple mornings, and then it uses that to adjust things now. So if your building's going to go occupied at 8 a.m., instead of you saying, well, let's put the schedule at 6 a.m., that way we know we're covered, you put 8 a.m. in there and let the thermostat figure out what time do I need to start to get the building warm enough or cool enough by 8 a.m. And then it might start at 7:53 because it's a super mild day out and 7 minutes is all it needs. Or it might start at 6:47 because it needs an hour and 13 minutes to get there because it's a cold day out or whatever. Every time it doesn't start as early as you would have put in, it's saving you minutes of each of those days of runtime, which saves you hours a year, which saves you tangible dollars. It's super easy to do, and every high-end stat has it. It costs like $10 more than a regular stat. You have to have two-stage thermostats. All thermostats at commercial buildings need to be two-stage stats. It's going to be required when we talk about integrated economizer in a couple minutes. So for right now, just know that it has to be two-stage. I'll explain why in a little bit. You want to get a stat that'll also shut off the ventilation system during unoccupied hours. This is required by code on modern systems, but people don't really understand it. The vast majority of thermostats out on the market do not do this. the thermostat at your building is not doing this now. Every time your thermostat asks for heating or cooling in the middle of the night, even though you have relaxed set points, it still opens up the ventilation damper because your ventilation damper doesn't know if it's daytime or middle of the night. It just knows the fan turned on, and if the fan turned on, it opens the damper. So what we need is an extra output on the thermostat, one that's not there now, that says, hey, economizer, you should be in the occupied or the unoccupied mode. So one extra wire goes from the thermostat up to the rooftop's ventilation input on the economizer and tells it it's daytime or nighttime, or occupied versus unoccupied time. And if it's unoccupied, we shut the damper. Because I don't want to bring any ventilation air in for a building that doesn't have any people. There's no point in doing that. We talked about that last week. You only have to ventilate if people are there. Now, maybe you want to start the ventilation a little bit early. That's fine, right? But I don't want to start the ventilation or have the ventilation go all night long, right? There's no reason to ventilate at 2 in the morning when no one's there. This is required by code now. I would say less than 2% of the buildings I've been to have had this, whether it's code compliant or not. And it's super easy to do. It's a thermostat that, once again, costs like 10, 15 bucks more than other thermostats, and it's an extra wire. Mike asks, what about going into setback an hour before building officially considered unoccupied? That'll save more energy. So if your building's going to go unoccupied at 5 p.m. and you want to go on to the unoccupied set points at 4 p.m., it'll save more energy, right? It's an extra hour of relaxed set points. The debate you'll get into is if you need to ventilate during that time frame. That's going to be your challenge, because for ventilation code, you're probably going to want to do that. Now, technically, most ventilation codes allow you to have up to 2 hours of occupied time that's not ventilated. Typically, that's meant to be like for transient spaces. Like if you don't want to ventilate your hallways, you don't necessarily have to, because people are only there for a couple minutes. It's not really meant for this. People try to shove it down that way. So you should probably continue ventilating your building all the way till the 5 p.m. time or whatever time you establish. So there's not really many thermostats that can do both of those things. A building automation system you could decouple the ventilation schedule from the temperature schedule. But for most systems, those are one thing and the same. So you're probably going to let it go all the way to 5 p.m. Different, interesting question you had there. You can make the stats internet accessible. This in and of itself typically doesn't save any energy, but it's going to make things easier to be done. And one of the problems we had is that programmable stats is not easy. That's why people don't do it. And if I can make it dumb and easy, then maybe you'll do it. Because you're probably like me. You don't want to do anything that takes more than 5 minutes. Paybacks on programmable stats are really, really fast. I put on here 6 months. The bigger the system, the faster the payback. So if you have a 100-ton single zone constant volume rooftop, the payback on this thing would be in weeks. If you have little 3-ton rooftops, the payback may be 18 months, right? But for purpose of most of my slides and discussion, I'm thinking about stuff that's like 10, 15 tons, kind of in that middle range. I used to put thermostats back. Well, I used to put building automation systems. Well, we used to put them on modems in the 90s. Then around 2000, I started hooking them up to the internet. But around 2005, it became feasible to put thermostats, regular thermostats, on the internet. You guys in Massachusetts may actually recognize these stats. I was buying them from Massachusetts from a company called Prolifix. I think they're probably still around. They probably have better looking stats than this now. And I was using their stats for a couple years. The only problem with their stat is I had to hardwire it from Ethernet back to the router, which made it a little bit hard from an install standpoint. And then 2-3 years later, everybody came out with Wi-Fi stats, and that made things a lot easier. But even back then, 2006, it was pretty easy to put thermostats on the internet. Sure, this one's 15 years old, so the graphics are old and ugly, and the new ones are better. But it has all the same basic info: zone temperatures, scheduling, some basic alarms, stuff like that. And when I would show people this scheduling, the first thing they would say is, "Holy crap, that's a lot of stuff." I'm like, "Yeah, it's a lot of stuff." But it's the same stuff you were trying to do before from the screen of your thermostat. Monday, next screen, 7 a.m., next screen, 72 heat, next screen, 75 cooling, next screen. Okay, let's do the daytime for Monday, then the evening, then the night, then Tuesday, then Wednesday. By the time you got to Wednesday, you were done. You turned it off. This made it way easier for people to do it. And now it's even easier with smart stats. You can even not even program them. You can get ones that have motion sensors. And if the room's occupied with motion, we go to the occupied set points. If it's not, we go to relaxed energy saving set points. You can get ones that have geofencing. That doesn't work for large buildings, but for a small office building or a house, you can have geofencing. When your phone drives outside the perimeter, we go to the unoccupied set points. When it drives in the perimeter, we go back to the occupied set points. If anybody wants to take a deep dive into programmable smart thermostats, let me know. I'll get you a whole recorded 1-hour webinar on just that topic alone. I did it last week for somebody. I can send you the recording. Actually, I do it pretty much every month, but I'll send you the one from last week if you want. In the interest of time, I want to get to economizers, though. You can also go to full building automation system. This is not super common for these small package systems because you typically only have 2 or 3 units. So it's kind of like, well, for 2 or 3 rooftops, do I need a full building automation system? Probably not. But what if I have 2 or 3 units at my buildings and I have 45 buildings? Well, now I might want to have a building automation system and network them all together. Or maybe I have a lot of rooftops at one building, right? Or maybe I don't have rooftops. Maybe I have chillers or boilers and all that stuff. So I can go to a full building automation system. It's just going to be a little bit more upfront cost, but the bigger or more complex my building gets, the more likely I'm going to want to do it this way. And then I can have a lot more stuff integrated into here. But a lot of this stuff is available in thermostats now, like this monitoring the health of the equipment. My Ecobee stats do this now. I'm not pitching a specific brand here because I don't really care what you guys buy. It doesn't matter to me in any way. But I like to use the Ecobee ones because there's all kinds of trending data and graphs, and I can dump it in Excel, and I'm kind of dorky like that. But one of the things it'll do is I might get an email from one of my thermostats, and it'll say, hey, we've been trying to heat this system for the past 3 hours, and the temperature actually went down a degree. Something's broke. It doesn't know what's broke. It just knows that's not normal, right? So maybe it's polar vortex day. Maybe it's negative 28 out. Okay, fine. But that's probably not the case. It probably means something's not running. And maybe it's not a bad enough day out that the occupants know it yet. It's kind of mild out. So they haven't really got to the point of complaining. If I can know a day or two before they complain, why would I not want to do that? So those alarm messages can be pretty helpful, and collecting data is awesome. Somebody says, oh, every Tuesday morning my system does this weird thing and it gets super hot in here and I don't understand why. Something's broken. I can go look at the trend data and be like, well, every Tuesday morning your set point gets jacked up to 90 degrees for heating for an hour. That's why it's so hot in here. Well, why the hell is that? I don't know. I don't know why you programmed that in, but let me undo it for you. All right, it's pretty easy to go look at some of that stuff then if you have the trend data. If you didn't know, for energy code compliance, you have to use programmable stats. It's not even an option. You have to use programmable stats. They have to be 7-day programmable. Those 5+2s don't count. By the way, a 5+2 is a residential stat. No one's ever made a commercial thermostat that was 5+2. All the commercial ones are always 2-stage. They're always 7-day programmable. Anything else is a residential stat being put into a commercial building. You must have at least a 5-degree deadband between the heating and cooling set point. That means if your heating set point is 70, your cooling set point needs to be 75 or higher. You cannot make them closer. People do it all the time. They have to do it all the time because their system's oversized. They need to do is dehumidify, but it's not allowed by any of the codes. You can't have overlapping set points. You have to have a way for the occupants to override the set point. If not, they're going to bring in space heaters and jack stuff up anyway. You have to do that intelligent recovery I talked about where it starts early. That's required by code. You have to shut the ventilation damper at unoccupied times. That's required by code. And then you have to do what's called FDD, fault detection and diagnostics. I'm going to show you that on the economizer discussion, but the thermostat has to be part of that discussion. There's only like 7 or 8 models of stats in the whole country that comply with everything on this list. So if you're going to use a thermostat instead of a building automation system, it's a very short list. I can send you that list. It's like 1 Ventstar model number, 1 Carrier model number, and like 4 or 5 Honeywell model numbers. And that's it. Everyone else can't do all these things. It's pretty limited. They might do almost all these things. They may say that they're Title 24 compliant, which makes it sound like you do everything because California people are always the most strict. Well, they're not in this case. California is actually less strict. To do everything on this list, Title 24 isn't going to cut it. You have to do more than that. Your thermostats can also help out with demand charge. Not every thermostat does this, but some do. Some of them will stagger the start of the equipment. So if the equipment's all supposed to come on at 7 a.m., it may start one unit at 6:45, another one at 7, another one at 7:15 to stagger the start. When I first turn a piece of equipment on, if it's an inductive load, so like a PSC style motor, when that motor or compressor, when that thing kicks on, it has an inrush of current, and then a couple tenths of a second later that drops down. I'd like all those peaks to not happen at the same time. It'll lower my inrush current, and it'll make it less likely that that affects my peak demand. You can do this manually with your thermostats as well. In this case, I have 3 thermostats, and we're starting them all at different times. In this example, they have a 50 kW demand and a 25 kW runtime. So if I started them all at the same time, I would get an inrush of 150. Right? If I happen to start them all at the exact same time. If I started staggering them out, I can break that down. So I might have 50 if it comes on with just one unit, boom. And then that unit continues running at 25. The next guy comes on with 50, that's 75. And then when the third guy finally kicks on with his 50 inrush, I have 25, 25, and 50, so it's 100. So I can make my inrush lower by staggering the start of these guys. Some of the utilities have rebates for thermostats as well, for programmable thermostats. All right, economizers, the last main topic that we really want to dive into today. There's a couple quick questions here. Reza asks, does the damper open during unoccupied time for free cooling? I'm assuming you're talking about if I tie an occupancy schedule to my economizer damper. Most people don't do that, but if I did, like the code requires and like I would want to do to save energy, yes, the damper can still open for free cooling mode. So what that does, when that economizer gets the signal for occupancy, what it does is it lowers the minimum damper position from whatever you set it for code compliance, like we talked about with this screen right here last week. It changes it from that down to 0 for the minimum. Then during the daytime, the damper for an economizer mode can modulate between minimum and 100%. At nighttime, it can modulate between 0 and 100%. So for you guys that joined us last week, just know the short version is for every state and or municipality, there's a mechanical code, and it's probably based on ASHRAE 62.1 or the International Mechanical Code. In either case, it would have tables like this, probably 4 or 5 pages worth. In my example last week, I used an office building, which required 5 CFM per person plus 0.06 CFM per square foot. And those two numbers get added together, and they only apply during occupied hours. During unoccupied hours, you can go down to 0. And in fact, for the energy code, you have to go down to 0. You can do this with just a regular manually positioned damper. You can do it with a motorized 2-position damper like I'm showing here, or you can do it with an economizer. You're probably going to do it with an economizer. Mike asked a question, what % of commercial buildings have OA dampers that do not close when unoccupied? I don't have any statistical data, but it's well over 90% in my observation, looking at a few thousand buildings over the past 20-some years. It is very, very rare to find a building that has dampers that shut during the unoccupied mode. Buildings that have a building automation system are much more likely to do that. Buildings that have thermostats, probably not at all. Even buildings that were installed under the current codes, and IECC 2018 and 2015 both require this, and I think even 2012, but I have to go back and look. So let's just say the past 10 years this is code required, and almost nobody has done it. At my office, we always bid the rooftop units, because we're an HVAC distributor. We bid the rooftop units with a code compliance stat that can do this, and almost none of those stats get hooked up correctly. We bid it that way, we give them the more expensive stat, we ship it that way, we give them the links to the videos on how to do it, and then later on when I go to the job sites, they haven't done it. So I would say almost every building you go to, assume it's not done, especially if it's regular thermostats. And it's pretty easy to add it on. All right, outside air economizers. This is really important because this is probably the third best thing that I could do to save energy in a building. Putting it on a schedule is probably number 1 because it's super inexpensive to do that. That's probably number 1. Getting the fan to be more efficient, which we'll talk about next week, is probably number 2. And then getting this free cooling is probably number 3. So a lot of commercial buildings need cooling when it's cold outside. The example I like to give to building owners is, hey, let's just say this is your house. And let's say you're going to host Thanksgiving. The wife says, hey, we're doing Thanksgiving at the house this year. 45 of my relatives are coming over. And you're like, yay, love it. Super excited about that, honey. Right? Well, everybody's cooking. You're using all the burners. The oven's going. People start piling in the house. Even though it's 30 degrees outside, it starts getting warm in there. You're like me. You're cheap. You're not turning on your compressor. So instead, you open up some windows. That's what you normally do at your house on those kind of scenarios. Well, in a commercial building, we have lots of days in the fall and the spring, and even in the winter sometimes, where the building needs cooling, but it's already cool outside. Right? I have a lot of people, a lot of lights, a lot of whatever. If it's cool outside, why don't I just open up the window and not run my compressor? Great idea. Let's do that. Oh, wait, I glance over at my windows. They're not operable. How am I going to open the window? So instead, what I'm going to do is I'm going to open up a window in the mechanical equipment, in the rooftop unit, and use the fan in the rooftop unit to suck outside air in and use your duct system to deliver that cool outside air. If I want to cool the building and it's 57 degrees outside, don't turn the compressor on, just suck the cold air in. Boom, done. That's exactly what an economizer is. It doesn't have to be explained any more complicated than that. However, for your benefit, I'm going to explain it more complicated than that. So in order to control this, I need a system to do this, not just a damper actuator to modulate this damper, but I also need something to control the system. And in other words, decide, is it nice outside? For Thanksgiving, you knew it was. You're hot inside. You already know that it's cold outside. Just go ahead and open up the window. Open it up. Just do it, right? Well, if I'm going to automate this, I have to define what nice outside means, what cool outside means. So there's 3 ways we can do that for most building types, at least here in the Northeast and in the Midwest. The main normal way to do it is what's called a dry bulb economizer. That means I'm just going to look at the straight up temperature. I don't care about humidity, not my problem right now. Dry bulb economizer, dry bulb temperature. So I have an outside air temperature sensor sitting on this unit, and if my system asks for cooling, and I look outside and let's say, for example, it's less than 60 degrees out, don't turn the compressor on. Just open up the damper and give me the free cooling. But if I look at it and it's 82 out, well, don't do that. Sucking 82 degree air in isn't going to help me. I'm already hot. Leave the damper at minimum ventilation position and run the compressor, right? That's how that's going to work. Now, the problem is sometimes if I have temperature that's cool, but it's also like rainy and humid, I don't want that. That's not good. So I can take a step up and I can go from a dry bulb economizer to what's called an enthalpy economizer. Enthalpy, if you don't know, is the sensible plus the latent energy. We'll talk about that more next week as well. But for right now, just consider it to be temperature and humidity. If the temperature is low and the humidity is low, go ahead and use the economizer for free cooling. The third way I can do it is differential enthalpy. So this box right here is representing my package rooftop unit. I'm sucking outside air in here. It goes through my filter, goes through my cooling coil, goes through my fan, gets delivered down my duct system to all my rooms. And then I have return air coming back, right, which mixes with my ventilation air and goes through again. So if my system wants cooling and I want to do differential enthalpy, I can look at the temperature and humidity of the outside air and look at the temperature and humidity of the return air. And if the outside air is cooler and drier than the return air, I don't care if it's 80 degrees. If it's 80 degree air outside, but my return air is 85 for some reason, well, 80 sounds nice. Let's take the 80 degree air. It's cooler than 85. Differential enthalpy means take whichever airstream is cooler and drier. Now, with 80 degree outside air, I'm still going to have to run my compressor, and we'll talk about that in a minute. But I'd rather start with 80 degree entering air than start with 85. So the way the sequence works for an economizer is the thermostat on the wall asks for cooling. He doesn't give a crap where it comes from. He doesn't care if your compressor runs. He doesn't care if your damper opens. He doesn't care if you walk in the room with buckets of ice and blow fans on him. He doesn't care. He wants cooling. He closes the relay that says, give me cooling. That signal goes up to the circuit board up in the rooftop unit. But what ends up happening is it doesn't go there on an economizer job. Instead, that signal gets intercepted and run over to the economizer damper controller. And then that guy looks at the outdoor conditions or the differential conditions, depending on what system you have, and decides, is it nice outside for free cooling? If it's not, and it's too warm outside, it says, okay, I'm going to go ahead and pass that signal you gave me over the compressor and run it like you want. So the thermostat asks for the compressor to come on, or it asks for cooling. The economizer gets first dibs on that. And if it says, no, it's not nice out, it's too hot out, or it's too humid out, don't do it, then we go ahead and run the compressor like a normal system. But if it is cool out, then we don't run the compressor. And instead what we do is we start modulating this outside air damper to provide me cool air. I'm going to put a sensor in the system. Typically it gets mounted over here in the fan section. It could be mounted in the supply duct, but that's rare. It's typically mounted in the fan section. On large systems, so bigger than a packaged rooftop unit, we typically get a sensing element, a mixed air temperature sensor that goes down in the middle over here. But on small systems, it ends up being a small, tiny sensor that gets mounted in the fan cabinet. So thermostat asks for cooling. Economizer says, yes, it is nice outside. Let's do this. He starts modulating the outside air damper to maintain 53 degrees right here. Then I get a degree or two of waste heat off of the motor, which means I end up with 55 in the supply duct, which is what the vast majority of cooling systems are designed to provide with their compressor anyway. If I can get you 55 degrees in the supply duct with the outside air damper, there's no reason to run your compressor. I'm good. I'm covered. Done, right? We'll skip those for now. Economizers are code required. For the International 2018 code, for energy code, if the system is 54,000 BTUs and larger, what does that mean? That means 4.5 tons. So 4.5 ton systems and larger have to have an economizer. Systems that are smaller than that do not have to have an economizer. There are some exceptions to that rule. Most of those exceptions do not apply to you. They're niche-y things. Like if you have a special process application for humidity, okay, that's fine. That's not a normal building, right? If you have a supermarket with refrigerated cases, okay, that's fine. That's not a normal building. For normal building, meaning office, retail, school, that kind of stuff, you have to have an economizer for 4.5 tons and larger. The exception that does come up sometimes is number 3. Systems expected to operate less than 20 hours per week. That comes up like on churches and stuff like that. We're like, dude, I have like 2 services on Sunday for an hour and a half each, and I have 1 service on Wednesday, and that's it. Other than that, I turn this thing off. All right, fine. If you don't want an economizer, you don't have to get one. By the way, it probably still would pay off because of the large amount of people in there, but that's fine. If you don't want to buy it, you're not required by law to do it because you don't have a lot of run hours. The other thing that the code does is it dictates to us the set points required for the economizer. Right? I'm going to skip over here for a second and look at this map. So if you haven't seen this map, this is the weather map that all of the energy codes use. For everybody's energy code, pretty much uses this map. And it gets tweaked every 10 years or whatever, but this is basically the map. So for you guys that are in Massachusetts, you are in green. My friends in Illinois, you're in green. My Wisconsin guys on the call, you're in blue. I saw there's a few New Hampshire, Vermont people. You might be in blue depending on which county you're in. You got to look at the details of the map. But you're probably in green or in blue. That means 5A or 6A. Everybody on this call, I believe, is in 5A or 6A. If you're in Miami and I missed you, sorry about that. All right? So 5A, oh, my mouse locked up. That's not good. All right, well, if you're in 5A or 6A, as soon as my thing responds, there we go, you'll be on this line right here. So if you have a dry bulb sensor for 5A and 6A, you're required by law to set it for 70 degrees, meaning if it's less than 70 degrees, you have to use the economizer. If it's above 70 degrees, you do not use the economizer. That's a challenge because historically, most guys have set it up for 55, right? Because their logic was, well, if I'm at 55 anyway, if I can make 55-degree air here, then I don't even need to run the cooling, so I already got 55-degree air. And when I started in the field in the 90s, we always set it for 55. And by the 4th job, I'm like, hey, Gary, why do we always set every job at 55? He's like, dude, stop asking so many questions. Just set every job at 55. I'm like, but why is it different? He's like, stop asking questions. Always 55. Just do every job the same. Like, if every job's the same, why is there even a setting? Dude, 55. All right? So what do? I set it for 57, 58, 59, 60, 62, 65. Whoa, time out. 65 was a problem. 65 didn't work. I would get calls saying it's too humid in there. But 62 and less, I was good. Never had a call back on 62. So I just set every job at 62 instead of his 55. And at 7 more degrees of outside air, which is several hundred hours per year for most climate zones, then I got free economizer cooling. Well, now the code says at 70. I know that between 62 and 70, I'm going to have complaints. I know it. I've had enough jobs to know. But that's the law. That's what I got to set it for. Technically, I could set it for 68 because if you look down here, it allows you to have a 2-degree span on there. So 70 is defined as anything between 72 and 74. That would be compliant. If I want to do an enthalpy economizer, then it goes from 70 to 75, meaning I got to take air on a 73 or 74 degree day. But I also get to babysit the enthalpy, i.e. the humidity. And if it's 28 BTUs per pound, then I don't have to do it. There's a plus or minus 2 on that guy too. So what does that look like? All right, so this is a psychrometric chart, and this may be more than you guys bargained for when you signed up today, but I'm going to show it to you anyway. And I'll give you kind of the quickie version. If you want a 3 or 4 hour class online of just psychrometrics, let me know. I can send you a link on that as well. Every time I'm saying I'll send you a link, write down my email, send me a link, and sometime today or Monday I'll send you something. It's Ryan, R-Y-A-N, .Hoger, H-O-G-E-R, at TEC, Temperature Equipment Corp, TEC, Mungo, M-U-N-G-O.com. And I'll put that back up at the end again in case you need it on the screen. Send me a note, and I'll try to send you whatever I promised you, because every time I do a presentation, I promise like 40 things. I don't remember what I promised. So in any case, this is psychrometrics. The simple version right now is these vertical lines are temperature, dry bulb temperature, no moisture involved. 50 degrees, 60 degrees, 70, 80, 90. The horizontal lines are moisture, humidity, 140, 100, 60 grains of moisture. It is not relative humidity. Grains of moisture are actual moisture. So the way I visualize a grain of moisture in my head is it's a droplet of water. It's not that measurement. It's a grain. But in my brain, it's a little droplet, right? Ooh, little droplet. That's a grain of moisture. And if I took a box of air and I counted up all the droplets, how many grains of moisture would I have? That is not relative humidity. Relative humidity is totally different. Relative humidity on this chart are these curved lines, 40%, 50%, 60%, 90%, and then this last line here is 100%. 100% means the air is completely saturated. That means it's holding as much moisture as is physically possible. It couldn't take one more drop of moisture if you begged it to. If you gave it one more drop of moisture, it would drop out and condense on some cold surface, right? Water bottle, beer can, car windshield in the morning, dew on the grass. That's all condensation because you got to the 100% dew point mark. And we don't even bother building a chart over here because for HVAC, we can never be super saturated. We can never be more than 100% for air, so I don't care. Not my problem. All right, so 100% is this last curve. 100% means that's as much moisture as that air can hold at a certain temperature. Warmer air can hold more moisture. So if I looked at 55 degrees, my red dot right here, I could hold 63 grains of moisture. If I looked at 70 degrees, I could hold 110 grains of moisture. If I looked at 85 degrees, I could hold 170 grains of moisture. Warmer air can hold more moisture. So the percent means how close to saturated am I? 50% means I am halfway to being saturated. But 50% means something different on a cold day versus a hot day. So if someone asks you how humid it is, 50% is useful in terms of how well my body can sweat to the air. And that's a whole other discussion. That's another 3 or 4 hour webinar on the way your body rejects heat. So let me know if you want that, on how good I can sweat the water from my body to the air. But it doesn't really tell me how much moisture is in the air unless you tell me the temperature. So if I take the traditional 55-degree economizer set point that every technician has done for 40 years, this black line, everything to the left of that would be an economizer day, meaning do not use your compressor. Use the free cooling from outside, open the damper. Everything to the right would mean do not use the damper, run the compressor. Well, with the current code, that black line moves to this yellow spot. That means I have to take 60, 65, 68 degree air as my cooling days. That's okay. I probably can't cool your building with 68 degree air, but it's a good starting point, and maybe I run a compressor to supplement it, and I'll explain that in a second. But look what happens over here. If I had a 90% humid day when it was 55, that's 60 grains of moisture. But if I had a 90% humid day when it was 68, that's 100 grains of moisture. It's almost double the amount of real moisture. Well, why does that matter, Ryan? It's only 90% humidity. Yeah, 90% humidity at those temperatures. When it comes into the building, it's all going to be the same temperature as my indoor temperature. And now I've got almost double the amount of moisture, which is going to cause humidity complaints in the building. If you suck in air right where my red dot is, it's going to cause a humidity complaint in the building. I promise you. I refer to this space right here as the triangle of death. If you take that air in on an economizer day, people are not going to be happy with you. That triangle over here was not a problem because it wasn't a lot of real moisture. It was a high percentage, but not a lot of real moisture. Up here, it's a problem. So avoid the triangle of death. And the way we're going to do that is by using enthalpy. So if you don't know on the psych chart, these little tiny lines over here, those little numbers that you can barely see probably, those are enthalpy numbers. It's basically temperature and humidity combined, which is why the line is on an angle. All these white lines on an angle are enthalpy numbers because it involves the moisture and it involves the temperature. If I go to the code number of 28 and I draw that line out, now if it's to the left and below of this, that means it's an economizer day. If it's over here, too hot, non-economizer day. Over here, too hot and too humid, non-economizer day. Over here, too humid, non-economizer day. So I essentially get rid of the triangle of death. I did have to move my line from the 70 to the 75 number, so I got to take these days as economizer days, which is great, but I don't have to take these humid days. trade them off. That's why you're going to want an enthalpy economizer. We used to do it because you could save a couple bucks more per year. Not an exciting reason, so we didn't do it a lot. But now, if I want to comply with code, I almost have to do the enthalpy one because the temperature only one is going to be a complaint job. Or I got to do temperature only and then cheat and not follow code and set it for 62 or 63 instead of setting it for 70. I'm not saying you should do that. I'm just saying if you pick the wrong economizer control and you do dry bulb, you're going to end up going back and either putting an enthalpy sensor in or cheating the code. One of the two. The code also requires you to have an integrated economizer. What does that mean? That means you have to run the compressor in conjunction with the economizer when it's appropriate. This is the way I like to graph that out. If it's below 55 degrees outside, my old traditional black line, most systems are designed to provide 55 degree supply air, so it's below 55 outside, I probably don't need a compressor. My economizer should get it all done all by his lonesome. If it's above that 75 or above my 28 enthalpy, well then I'm not even going to try the economizer. I'm just going to use the compressor only, so I'm over here. And then anything in the middle is going to be my integrated economizer time, meaning I'm going to possibly run the economizer at the same time as the compression. Essentially what's going to happen is the economizer is going to become stage 1 and the compressor is going to become stage 2. That is why you must, I repeat, you must always have a 2-stage thermostat for all commercial systems. Even if you only have 1 stage of compression, you still got to buy a 2-stage and wire a 2-stage thermostat. Because when I have an economizer, if it's nice outside, stage 1, Y1 off the thermostat, becomes my first stage of cooling. And Y2 off the thermostat, stage 2, becomes my compressor. So I always got to have a 2-stage stat on an economizer system. Most of the economizer controls have enthalpy curves on them. This is showing a modern control, which is the JADE control, which is the code compliant control that almost every manufacturer uses. Some of them use a Belimo zip controller. Some of them use their own Johnson controller. But the vast majority of manufacturers use Honeywell, just the way it is. And these are the curves that are pre-built into that system. They have curve 1, 2, 3, 4, 5. Their old stuff from the 90s and 2000s had A, B, C, D. Those curves are unrelated to these curves. They look completely different. We don't need to talk about them right now at all. Just know you're going to follow one of these curves. And if I want to go with a code compliant, see, I'm going to plot that yellow line back on there. That's the code compliant curve. I'm going to plot these purple ones on to show the plus or minus 2 BTUs and the plus or minus 2 degrees. So anything between the 2 purple lines is code compliant. So essentially, I'm going to recommend that you pick curve 2. That's almost the code compliant line. There's no line that's exactly code compliant, so I got to choose 1 or 2. 2 is the most code compliant in my opinion. Plus, I don't want 80 degree air, so that's the one I'm going to pick. If I go back to that same software tool I was using before, right? So I have a basic unit. I have this says 2015 code compliant unit. 2018, as far as the equipment efficiency table goes, is the exact same code compliancy. So I didn't update my slide here, but this would be the same for 2018. I would still need to be the same efficiency here, 11.5 EER and whatever the IER was on the backside. So basic, simple, low-end unit that's not code compliant, but current unit, code compliant unit with an economizer. So just going from that basic unit to the code compliant unit was, in this project example, whatever example I picked, I think it was a 8 or 10 ton rooftop unit for an office. It was a $37 savings, 1%. Adding the economizer was another 8%. An economizer will save significantly more efficiency than going to a high efficiency unit. High efficiency units are not that exciting in the grand scheme of things. I'm not saying you shouldn't get them. I'm not saying they're not valuable. I'm just saying if I have to choose how to spend my dollars, I would rather get a less efficient unit with an economizer than get the most efficient unit. Now, from a code standpoint, both are required, so what's the difference? But I'm just pointing out how valuable that economizer really, truly is. If I'm going to suck extra outside air into the building, I need to have a pathway to get extra air out of the building, right? I can't just suck air in and then the building blows up like a balloon and explodes. That doesn't make sense. So if I don't give it a good pathway out, it'll find its own pathway. And frequently that means the very front doors. The front doors will have trouble shutting them. When you're on an economizer day, you suck a boatload of outside air in, and then your front door won't shut. And you literally have to like pull it with your hands. It's ridiculous. So instead of doing that, I need to find a pathway to get it out. There are lots of possible pathways The most common ones are to do it with the same rooftop that's sucking the air in. And the most common way to do that on a small, simple system is a barometric relief. What is a barometric relief? It's just a piece of sheet metal hanging there. And when the pressure in the building builds up, instead of pushing the front door open, it pushes this damper blade open. That's it. It's not anything smarter than that. That's why we do it on most systems. If the system gets big, and by big I mean the ductwork gets long and restrictive, then the air in the room that I have for that pressure says, I can either go out that 145 feet of duct to get to that barometric damper Ryan put in, or I can go 13 feet to that front door. Air is lazy. Path of least resistance. It goes to the front door. So if my return ductwork gets long and restrictive, instead of having a barometric relief, I'm going to put a power exhaust fan in there and suck the air out of the room. So I'm going to have a fan sucking air in, and I'm going to have a fan sucking air out of the building. And the more I open the damper, the more I'd like to turn that fan on. I'm going to skip that one for today. It's more complex than we need. Got 15 minutes left here. Do like 300 more slides. No, I'm just kidding. We still have next week to do the other half. The energy code will also require all of my mechanical inlets and outlets of the building, so all my exhaust dampers and all my outside air intake dampers, to have low leak motorized dampers. So low leak is not just a random thing. It's a defined thing. For the international code, the definition of it, if you read up here, not that I want you to read all these code things, but the definition of it is that I have to have no more than 4 CFM per square foot leakage at 1 inch of pressure. That's the definition of it. And to do that, I'm going to have an AMCA certification and an AMCA 500D stamp on the metal, saying that it, or sticker, saying that it complies with this. Once again, California Title 24 code does not comply with this. Title 24 has a thing called a low leak damper. It is not low leak enough to be compliant with this. So once again, pay attention to that. Some of the manufacturer dampers, you'll ask them if it's low leak, they'll say yeah. You'll ask them if it's certified to be low leak, they'll say yeah, it's Title 24, bro, it's good. Yeah, but it's not compliant with IECC, meaning it's AMCA certified. Not good enough. So we've got a couple examples so far where California is not as good as everybody else per se. I'm sure they're going to leapfrog us again because they always do that, but that's how it goes out there. There are some exceptions to when you don't have to do this, but as soon as there's a motor on there, you have to do it. And all economizers have a motor, so for all economizers, they have to be low leak. From a visual standpoint, you can easily tell for most systems, rooftop systems, if you have a low leak. If you have a regular damper, the gears, these little gears with the little teeth on them, right? The gears will be on the inside over here in the airstream. If I have a low leak one, the gears move from the inside of the airstream to the outside of the airstream. The reason being, when they're on the inside of the airstream, gears obviously have to be able to move. If they have to be able to move, it's difficult for them to be perfectly tight. And if they're not perfectly tight, it's really hard to get to the low leakage. So one of the 3 things that were done to make a damper low leakage are to move the gears from the inside to the outside, not the outside of the rooftop, just the outside of the airflow path, to put seals on the ends of the blades and on the edges of the blades. Those are the 3 things. Seals on the edges, seals on the ends, and then move the gears to the outside. You remember this we looked at before, and we said most economizers are a problem? So you're telling me the energy code says put all this economizer stuff in, even though we know it's going to suck and not be set up right or going to be broken. Yeah, that's what it said for years. And then, I don't know, 4 or 5 years ago, I think it was with the 2015 code, we added fault detection and diagnostics. We meaning the code people, not me. They added fault detection and diagnostics. This is the first thing in the code to have FDD as a requirement. The newer versions of the code coming out have even more FDD things, but economizers are the very first one to get it because economizers had this chart that said economizers suck. You guys are doing a bad job. So without reading the whole code to you, what it basically says is the economizer controller has to have the ability to babysit itself. It's got to check various things as listed here to verify that they're working or not. And if it's not working, it needs to notify someone. So for right now, just know that like a Belimo Zip economizer controller or a Honeywell Jade economizer controller does all these various different things. If you've got a building automation system instead, that's fine. Make sure they do all those different things. The interesting thing from the field standpoint is item number 6. That's the only one I want to read to you. The unit shall be configured to report faults to a fault management application available for access by day-to-day operating or service personnel. What's a fault management application? That's a building automation system. Somewhere it's got to notify the building manager that there's a problem on a day-to-day accessible basis. So it cannot be the screen up inside the rooftop, because we know you're not going to go look at the rooftop screen every single day. It's got to push it down to the building automation system where it pops up on the computer screen, or it shows up as a text message on the building operator's phone, something to proactively notify them. Well, Ryan, what if I don't have a building automation system? I just got a little 10-ton rooftop unit and a regular thermostat, and that's all I got. That's fine. There's an or on here. Or enunciate it locally on the zone thermostat. So if you don't send it to the BAS, you can send it to the actual thermostat on the wall that the building occupants will see. Now, most thermostats don't do that. That's a special thermostat. And that's why there was only like 7 miles of thermostat that comply with everything for code in our states. Because to do all the things we have to do with the set points and the setback and the occupancy interconnection to the damper, and now this fault management report going to the thermostat, only certain thermostats can do that. Like I said, there's a VentStar model number. Actually, there's 2 carrier model numbers now. No, there's one. There's 2. One VentStar model number, 2 carrier model numbers, and I forget if it's 4 or 5 Honeywell model numbers that'll do it. If you need those model numbers, let me know. I'm not pitching those brands to you because I'm not selling you anything anyway. But I have a list of ones that we maintain. I used to have it on the Illinois State website, but they have a new person managing that, so that's not on there. But I still have the old list. I can send it to you. It doesn't say what the thermostat has to do. It says enunciate it locally. So it could say anything. It could flash. That would count. It could say service equipment. It could say fault detected. It could say check engine light. Like, I don't care what it says. It just has to say something, right? And basically, it's a check engine light, right? So your car gets a check engine light. You have no idea what's wrong with your car. You just know that the crap hit the fan. I better bring it to the dealer. The dealer's going to hook their laptop up to it. They're going to pull out the data and say, oh, yeah, you have a broken oxygen sensor. We got to fix that. Okay, got it. Whatever the problem of it is. Or the last time I did it, yeah, your gas cap was still open. I'm like, are you serious? Jeez, right? That's a wasted maintenance call, all right? Same thing's going to happen here. It's going to flash service fault or equipment failure or something like that. The occupant's not going to know what the hell that means. They're going to call their HVAC guy. He's going to walk in and look at the thermostat and say, yeah, you got a fault. Cool. He's going to walk up to the roof, open up the cabinet, and then he's going to look at this controller screen and see what the specific fault is. Maybe it's the supplier sensor's out of whack, right? It's reading like -13. Well, that's obviously not right. Right, so we got to fix that sensor. Okay. From an economizer standpoint, remember I said I'd like to maintain the building 5 times a year, the equipment 5 times a year, or excuse me, 4 times a year. A couple of those times should include maintenance on the economizer. I like to cycle the damper all the way closed, all the way open, make sure it doesn't get bound up, make sure it physically moves. I like to double check the minimum airflow set point, and I want to check the sensors on that guy. Every 2 out of 4 times, right? So twice a year. Once going into the cooling season, once going into the heating season. I like to check it both times. Because if it's stuck open in the winter, it's sucking air and I don't want. If it's stuck open in the spring, it's not, or stuck closed in the spring, I'm not getting the free air that I want. Right? And if it breaks, no one's going to know. No one knows. Because the compressor just turns on. I call for economizer, damper didn't open because it's broke. Well, after a little while, I call for second stage cooling and the compressor turns on. And nobody knows. Right? So that's why we have to have this alarm on here, because it's a problem in the background that wastes a bunch of energy and nobody knows it's happening. And it happens a lot, right? So sensors, we talked about CO2 sensors being much better from a calibration standpoint. I joked about the enthalpy ones that we used to make them out of horsehair. We literally did. There was horsehair in there. And as it got more humid, the hair would deflect more and click the relay. Just like, well, I don't have hair, but like other people that have hair, their hair gets more curly or less curly depending on the humidity. Same kind of idea worked there. Nobody uses that anymore. It's all solid state electronics. It's much more reliable. I would still check the calibration of them, just like I do with the temperature sensors, but you probably don't have anywhere near the problems you used to have. The biggest issues are the operators. There are a lot of systems with 2x4s jamming dampers open. Over by where my office is, there's a convention center that we did building automation at. And I remember being on the roof one time helping those guys out with a problem. And I looked over, I'm like, hey, dude, why is that unit over there? What's up with the damper on that? What the F's going on with that 2x4? He's like, oh, yeah, dude, I kind of forgot about that one over on G Hall. Yeah, they had a problem there during a show, and we had to prop it open to get some airflow going because the compressor wasn't online, blah, blah, blah. I was like, well, when was that? He's like, I don't know, like November. I'm like, dude, it's February. That damper's been stuck open since November. He's like, yeah, I probably should do something about that. Yeah. I've had plenty of other jobs where the damper's been screwed shut, literally. Tech screws, zip, 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 screwed the whole thing shut. No fresh air, nothing. I'm like, dude, why is this damper screwed shut? He's like, oh, you won't believe it, man. I got promoted, so I'm not just the maintenance guy anymore. I'm also the energy manager. So if we save money on the utility bills, I get a bonus. Isn't that pretty sweet? I'm putting in all these occupancy sensors for the lights and stuff. And I went and saw that I was sucking all that cold air in the winter. I screwed that thing shut. Now we don't have to pay to heat it. I was like, yeah, but you're also not ventilating your building. He's like, oh, that's not good. I'm like, and you're not getting all the free cooling on the economizer, and your compressor's got to run a lot more. He's like, holy crap, dude, that's going to hurt my bonus. Like, this is the mentality of some of the people that are doing it. They don't know what they're doing, so they just do it. If you want to see how much outside air you're bringing in, I don't remember if I showed this to you guys last week or not. I think I did. But on a non-mild day, meaning on a cold day or a hot day, I can measure the temperature of the outside air, measure the temperature of the return air coming back to the unit, and then measure the mixed air. And then using this simple formula, I can figure out how much air is coming from the outside and how much is coming from the return. Right? So this is available to you if you want to try it this way. It's an easy way to measure the difference there. So this example is 10 degrees outside with 70-degree return air from the space. And it's a 50-degree mixed temperature. So after the outside and the return mixed, instead of 10 and 70, I had a mixture of 50. Well, mathematically, I can figure out how much came from each hole. So what's the difference in the mixed air return air? 20 degrees. What's the difference in the outside and the return air? 60 degrees. So 60 degrees would have been the maximum. If I had gotten this down to 10 degrees, that means all of it came from the outside and none came from the return. So the delta T with max was 60. I got 20. So I have 33%. 33% of my air is coming from the outside air. 67 is coming from the return air. If I know how much CFM that is, I'd have to know how much CFM the fan's moving. And if I don't know how much the fan's moving, which I might not, at a minimum, I could take an educated guess at the traditional 400 CFM per ton. If it's a 10-ton unit, that's 4,000. And if a third of that's coming from the outside, that's 1,300 CFM of fresh air. If my code only requires 1,000, that means I have 300 too much. I need to throttle my ventilation damper back and save some energy. And if it's too little, I need to open it up and provide better ventilation. A lot of the older economizers, you might only have two settings on there. Minimum damper position with a set screw. And then if it had enthalpy, I might have had an ABCD switch, which is the old version of curve 1, 2, 3, 4, 5. You probably won't see too many of these out there. I only pointed out because if you see this one, you cannot add a CO2 sensor to it like we talked about last week for demand ventilation. It's not possible. You have to retrofit the controller. But if you have a rooftop that has this old of an economizer controller, that probably means your rooftop's pretty old, which probably means you're a candidate for replacing the rooftop like we talked about earlier. If you have this guy, the 7200 series from Honeywell, this one says Carrier on it because they private brand it for lots of manufacturers, but almost all of them are made by Honeywell. There's 1, 2, 3, 4, 5 settings on it. So I still have that enthalpy switch on there if you have an enthalpy sensor. I have the minimum damper position switch. And then I have some switches for demand control ventilation with CO2, both a set point and a maximum throttle. Setting up the minimum damper position and the maximum set point for DCV is not intuitive, and almost every HVAC tech does it wrong and accidentally overventilates, which is crazy because the job of the CO2 sensor is to underventilate when people don't show up. Not underventilate, but ventilate less when people don't show up. If you need help with this, once again, let me know. I'll send you a link on how to do this kind of thing. But when you have DCV, the basic premise is instead of this being a minimum position and this being a max, let me get out my pen, it becomes a new minimum. So if you remember, like say for an office building, we required 5 CFM per person and we required 0.06 CFM per square foot, and I made you add them together. And you probably wondered why did they just do it, add it for me? Why is it separate? It's separate since 2004 for ASHRAE and 2006 for the mechanical code on purpose and specifically to aid in demand control ventilation. So if I had 100 people in this space on a normal job, I would need 500 CFM of outside air for the people. And if I say it's 10,000 square feet, which I think is the same example we did last week, I would need 600 for the building, for building off-gassing. And combined, I would need 1,100 for a normal building. And 1,100 would go here on the minimum damper position setting. However, when I have DCV, that is not the case. On DCV, 600 goes in there. It becomes my new minimum. And 1,000 goes over here. my new maximum, or excuse me, 1,100 goes here. And a DCV modulates me between these two things. My new minimum, which is the building part, and my regular minimum, which we call the DCV max to make you confused, is 1,100. And I modulate down from there when people don't show up for work at the building. And then because of the way these are labeled, it gets confusing. And people instead put the 1,100 on the minimum, and then they put something higher, typically 50% of damper position. I have no idea why they do that. They put 50% on there. And now this thing modulates between code minimum and something really high, instead of modulating between code minimum and something less. The new Jade controller doesn't do it this way. It's much more intuitive. So it's a lot better way to do it. But a lot of the existing systems have this. So you can put DCV on these. You just got to pay attention to them. And more than half of them are set up wrong like this, which means a lot of them are wasting energy, and people aren't seeing the benefit of the energy savings at all, which is crazy. I'm going to skip the DCV stuff in the interest of time because we did that last week. And I'm going to give you the last few wrap-up things. Well, that's my last wrap-up thing. Okay. So any other questions I need to answer? Let me do this. Pull this down. Why can't I hit escape? My computer locked up. I was just going to pull up the agenda for next week. Oh, something's on there. Okay, hang on a minute. Give me 1 second. That's why I made notes on there. Okay. All right, now you should see the agenda for next week. So if you're joining us next Friday, once again, 9 a.m. Eastern, 8 a.m. Central, the topic there is going to be staged air volume for packaged rooftop units and everything that goes with that, a discussion of heat pump systems, and then we're going to go into variable refrigerant flow technology. So that's next week's discussion. I'm going to stop the recording. I don't see any more questions right now. I told you I put my email address back up. So I will do that and leave it up for a minute. If you want to send me something, if I promise something and you want it, send me a note and I will try to hunt it down. All right. Thank you guys for your time, and I see most of you next week, hopefully.